In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. Let's start our video today with a potentially habitable world and dive into the temperate world of TOI 700d and the promise of nearby Earths. January 6, 2020. Just 18 months after the transiting exoplanet survey satellite, TESS, began its mission to find planets around the nearest and brightest stars, the team gathered to announce a discovery that captured the world's imagination. TOI 700d, an Earth-sized planet, orbiting in the habitable zone, around a small, cool star just 101 light-years away, close enough for detailed follow-up studies, bright enough for atmospheric characterization with future instruments. TOI 700d represents exactly the kind of planet TESS was designed to find, a small, potentially rocky world in the habitable zone of a nearby star. It's only the second Earth-sized habitable zone planet discovered by TESS, and it immediately became one of the most exciting targets for follow-up observations and atmospheric studies. This is the story of TOI 700d, a temperate world orbiting a red dwarf star, a planet that might, just might, teach us whether life can arise on worlds very different from our own. TESS, the transiting exoplanets survey satellite, launched in April 2018 with an ambitious mission. Survey 85% of the sky over 2 years, monitoring over 200,000 of the brightest stars near Earth, searching for planets through the transit method. TESS was explicitly designed as a follow-up to Kepler. While Kepler stared at one patch of distant sky and found thousands of planets, most were too far away and around too faint stars for detailed study. TESS surveys the entire sky, focusing on nearby, bright stars, stars bright enough that we can measure their radial velocities, characterize their planets' atmospheres, and conduct the intensive observations necessary for understanding planetary properties. TESS's strategy is methodical. It divides the sky into 26 sectors, observing each for approximately 27 days. The 4 wide-field cameras capture images every 2 minutes for selected high-priority targets and every 30 minutes for full-frame images containing hundreds of thousands of stars. This continuous monitoring allows TESS to detect planets through transits, the periodic dimming that occurs when a planet crosses in front of its star from our perspective. In August and September 2018, TESS observed Sector 2, which included a portion of the southern sky near the constellation Dorado. Among the approximately 15,000 stars in Sector 2 was TC 150428135, later designated TOI 700, the TESS object of interest that would become famous. TOI 700 was flagged by our automated pipeline because it showed regular, periodic dimming, the signature of transiting planets. Initial analysis revealed not one, but potentially 3 planets in the system, with orbital periods of 10 days, 16 days, and 37 days. The 37-day signal was particularly interesting because it placed the planet in or near the habitable zone. TESS's automated pipeline identified TOI 700 as hosting planet candidates in late 2018. But the initial stellar characterization contained an error that would temporarily obscure the system's true significance. When TOI 700 was first cataloged, the star's properties were misclassified. It was initially thought to be slightly larger and hotter than it actually is, a G-type star like the Sun rather than an M-dwarf. This affected the calculated planet sizes and orbital distances. It wasn't until several months later, when we obtained high-resolution spectroscopy, that we realized the star was actually cooler and smaller. an M dwarf, and that completely changed the planetary parameters. The correction was crucial. With the stars smaller and cooler than initially thought, the planets were smaller too, and the outermost planet, TOI 700d, wasn't just near the habitable zone. It was squarely within it. The correction came partly through professional follow-up, but also through an unlikely source: citizen scientists examining test data through the Planet Hunters test project on Zooniverse. Several amateur astronomers noticed anomalies in the initial classification and flagged the system for reanalysis. Their contributions helped prioritize TOI 700 for detailed spectroscopic follow-up. Citizen science plays a vital role in exoplanet discovery. Automated algorithms are good, but human eyes can spot patterns, anomalies, and interesting signals that computers might miss or misclassify. For TOI 700, citizen scientists helped ensure this system got the attention it deserved. Confirming the planets required extensive ground-based observations using multiple facilities around the world. We used the LCOGT, Las Cumbres Observatory Global Telescope Network, to observe transits of all 3 planets from multiple sites. This confirmed the signals were genuine transits coming from TOI 700 itself, not background eclipsing binaries or instrumental artifacts. We used high-resolution imaging at Gemini South and SOAR to rule out nearby stellar companions. And we obtained detailed spectroscopy to characterize the host star precisely. The radial velocity signal, the star's wobble caused by the planet's gravity, was too small to detect given the star's faintness and the planet's low masses. But statistical validation, combined with the lack of any plausible false positive scenario, gave confidence that all 3 planets were real. TOI 700 is an M dwarf, a red dwarf star, the most common type of star in the galaxy. Small, cool, and stable, it represents the kind of star around which potentially habitable planets might be most abundant. TOI 700 is what we call a quiet M dwarf. It doesn't show the intense flaring activity some younger M dwarfs exhibit. This is important for habitability. Frequent, powerful flares could strip away planetary atmospheres or sterilize surfaces with high-energy radiation. TOI 700's relative quiescence means its planets have a better chance of retaining atmospheres and potentially supporting life. The TOI 700 system contains at least 3 confirmed planets, all detected by tests through transits. Each planet has been characterized through combined tests and ground-based observations. What makes TOI 700d special is that it's Earth-sized and orbits in the habitable zone, the region where temperatures could allow liquid water on the surface, assuming the planet has an atmosphere. TOI 700b is too hot. TOI 700c is probably too hot and might be a mini Neptune, but TOI 700d sits right where conditions could potentially support life. In January 2023, astronomers announced the discovery of a 4th planet in the TOI 700 system, detected through additional test observations and careful reanalysis of the data. TOI 700e was hiding in the data all along. Its transit signal was subtle. The planet is smaller than TOI 700d, and its transits are shallower. But with additional test observations and improved data processing, we detected it. Remarkably, TOI 700e orbits between planets C and D, and it's even closer to Earth size than TOI 700d. The system now has 2 potentially habitable planets. TOI 700d is the 3rd planet from its star and the first to be confirmed in the habitable zone. Its properties make it one of the most intriguing, potentially habitable exoplanets discovered to date. TOI 700d is tantalizing because it's so close to Earth in size. At 1.19 Earth radii, it's likely a rocky planet. Planets below about 1.5 Earth radii tend to be rocky rather than gaseous. If it's rocky and has the right atmosphere, surface conditions could allow liquid water. The habitable zone is defined by temperature. Not too hot that water boils away, not too cold that it freezes solid. But defining precise boundaries is complex. For TOI 700, with only 2.3% of the sun's luminosity, the habitable zone is much closer in, roughly 0.12 to 0.23 AU, compared to the sun's habitable zone at 0.95 to 1.7 AU. TOI 700D orbits at 0.163 AU, placing it comfortably within the habitable zone's conservative inner boundary. The equilibrium temperature, assuming Earth-like reflectivity, is about 269 Kelvin, cold by Earth standards, but a greenhouse atmosphere could warm the surface above freezing. TOI 700D receives approximately 86% of the stellar energy that Earth receives from the Sun. This places it in a similar energy regime to Earth, though the radiation comes from a cooler, redder star. At 0.163 AU, TOI 700D almost certainly experiences tidal locking, a process where tidal forces from the star gradually slow the planet's rotation until one hemisphere permanently faces the star. Tidal locking dramatically affects climate. The day side receives constant starlight and heats up. The night side never sees the star and cools down. Without an atmosphere, temperature differences could be extreme, perhaps 400 K on the day side and 100 K on the night side. But if TOI 700D has a substantial atmosphere, winds would redistribute heat, moderating temperatures and potentially making both hemispheres habitable. Tidal locking also affects habitability in another way. A tidally locked planet generates less of a magnetic dynamo. Earth's magnetic field is partly driven by our planet's rotation. Without a strong magnetic field, stellar wind could gradually strip away the atmosphere. But atmospheric loss isn't inevitable. Venus has no magnetic field, yet retains a thick atmosphere. The atmospheric mass and gravity are sufficient. If TOI 700D is massive enough and has enough atmosphere, it could retain it over billions of years despite tidal locking. In the first scenario, TOI 700D is a rocky planet with a thin to moderate atmosphere, perhaps similar to early Earth or modern Mars. If TOI 700D has a mass of 1.5 to 2 Earth masses and is rocky, it could have a solid surface with continents and oceans. A thin nitrogen-dominated atmosphere with modest CO2 would create enough greenhouse warming to keep the day side above freezing. Water might exist as liquid on the day side and as ice on the night side, with a temperate zone at the terminator, the boundary between day and night. Such a world would be profoundly different from Earth. The sky would never lighten or darken. Eternal day on one side, eternal night on the other. The star would hang fixed in the sky, larger and dimmer than our sun, glowing deep red. Plants, if they existed, might photosynthesize under red light, appearing black or purple rather than green. The second possibility is that TOI 700D is a water world, a planet where water comprises a significant fraction of the total mass. Water worlds might form beyond the ice line in protoplanetary disks where water ice is abundant, then migrate inward. If TOI 700D has 20 to 50% water by mass, it could have a global ocean hundreds of kilometers deep, possibly with high-pressure exotic ice phases at depth and a thick steamy or cloudy atmosphere above. There would be no exposed land, no continents, no beaches. On such a world, life would need to be entirely oceanic or atmospheric. The absence of land-ocean interfaces where important chemical cycles occur on Earth might affect the development of complex ecosystems. But water is abundant, and in the right conditions, life might thrive. The third, less optimistic scenario is that TOI 700D experienced a runaway greenhouse effect and became Venus-like, hot, dry, and uninhabitable. Venus is in the Sun's habitable zone by some definitions, but it's anything but habitable. A thick CO2 atmosphere creates extreme greenhouse warming, with surface temperatures around 740 K, hot enough to melt lead. If TOI 700d underwent a similar runaway greenhouse, perhaps triggered by too much stellar radiation early in its history, liquid water would have boiled away, escaped to space, and left behind a thick, hot CO2 atmosphere. Determining which scenario is correct, or whether reality is something else entirely, requires observations we cannot yet make. But the tools to answer these questions are being developed. The ultimate question about TOI 700d, whether it's truly habitable, hinges on its atmosphere. Does it have one? What is it made of? And can we detect it? Detecting and characterizing TOI 700d's atmosphere is challenging, but potentially possible with JWST. The planet's transit depth is small, about 0.04%, and atmospheric features would change this depth by perhaps a few tens of parts per million. We need many transit observations to accumulate enough signal. But TOI 700 is relatively bright for an M dwarf, and TOI 700d transits every 37 days, giving us multiple opportunities. Different atmospheric molecules provide different clues about the planet's nature and habitability. Potential atmospheric constituents and their implications. Water vapor, strong greenhouse gas. Detection would suggest water is present, but doesn't confirm liquid surface water. Carbon dioxide, common in planetary atmospheres. Modest amounts consistent with habitability. Excessive amounts suggest Venus-like runaway greenhouse. Methane, on Earth, mostly biological, but can also be geological. Detection would be intriguing, but not definitive proof of life. Oxygen and ozone. On Earth, oxygen is produced by photosynthesis, a potential biosignature. But oxygen can also be produced abiotically through water photodissociation. Molecular nitrogen, major component of Earth's atmosphere. Not directly detectable in transmission, but affects mean molecular weight. Sulfur dioxide could indicate volcanic activity, which might help maintain a habitable atmosphere through outgassing. No single molecule definitively proves habitability or life. We need to look at combinations, the overall atmospheric composition, ratios of different gases, disequilibrium chemistry. For instance, oxygen and methane together in significant quantities would be suggestive of biology, because these gases react and shouldn't coexist without being continuously replenished. TOI 700d has been selected for JWST observations, though comprehensive results may take time as the telescope balances hundreds of competing science priorities. Multiple teams have proposed JWST observations of TOI 700d. We're using NIR spec and MIRI instruments to obtain transmission spectra during transits. Each transit gives us data at different wavelengths. By combining multiple transits, we build up signal-to-noise sufficient to detect atmospheric features if they're present. But this is a multi-year effort. We need patience. As of early 2024, preliminary JWST observations have been conducted, but comprehensive results have not yet been published. The analysis is ongoing, and the scientific community waits with anticipation. TOI 700d's significance extends beyond a single planet. It represents a test case for understanding habitability around M-dwarf stars, the most common stellar type, comprising about 75% of all stars. If planets around M-dwarfs can be habitable, that dramatically increases the potential number of life-bearing worlds in the galaxy. M-dwarfs are common, long-lived, and frequently host small planets. But they also present challenges: tidal locking, stellar flares, radiation in the early stages. TOI 700d is close enough and bright enough that we can study it in detail, testing whether M-dwarf planets can truly support life. Each of these planets tests habitability under different conditions, different stellar types, different radiation levels, different sizes. By studying them collectively, we learn which factors matter most. TOI 700d, being Earth-sized and around a relatively quiet M-dwarf, is an ideal comparison point. TESSA's primary mission ended in July 2020, but the spacecraft continues operating in an extended mission, observing sectors again with longer integration and discovering additional planets. The extended mission allows us to find longer period planets that weren't detectable with just 27 days of observation. We've discovered additional planets in known systems, including TOI 700e, and we're finding new systems entirely. Every additional sector, every additional year of data reveals more worlds, more chances to find planets where life might exist. If TOI 700d is habitable, what form might life take? Life on TOI 700d, if it exists, would face unique challenges. The constant red light from an M-dwarf star means photosynthesis would work differently. Organisms might absorb different wavelengths, appearing black or purple rather than green. Tidal locking means life would need to adapt to permanent day or night, or exist in the twilight zone at the terminator. And if the planet has a thin atmosphere, high UV radiation could be a challenge. Life might be microbial, living in the oceans or atmosphere, or it might be complex, adapting to the extreme environments. Perhaps simple plants and animals exist in the habitable zones, with specialized adaptations we can barely imagine. Or perhaps TOI 700d is lifeless, a barren rock or ice world, uninhabited and uninhabitable. We simply don't know. And that's what makes TOI 700d so exciting. It's close enough, bright enough, and interesting enough that we have a real chance of finding out. Within the next decade, JWST and future telescopes might detect biosignature molecules, or fail to detect them, telling us the planet is uninhabited. Either answer would be profound. Even with JWST, definitively determining TOI 700d's habitability or detecting life will take time. Atmospheric characterization is painstaking. A single JWST transit gives us limited data. We need multiple transits at multiple wavelengths to build up a complete picture. And interpreting the data is complex. We need to model stellar variability, account for contamination, distinguish biotic from abiotic signals. Even under the best circumstances, confirming habitability or detecting biosignatures could take a decade or more. But the effort is worthwhile. TOI 700d represents one of our best chances, perhaps our best chance, to determine whether life exists beyond Earth within the current generation. Just 101 light-years away, a distance light travels in a human century, orbits TOI 700d. Every 37 days, it completes another circuit around its small red star. One hemisphere basks in constant starlight, glowing red and warm. The other faces eternal darkness, cold and still. Between them, the terminator, where conditions might be just right. We don't know what TOI 700d looks like. We don't know if it has oceans or ice, atmosphere or vacuum, life or lifelessness. But we know it exists. We know it's Earth-sized. We know it orbits where temperatures allow liquid water. And we know we can study it. TOI 700d was discovered in 2020, at the beginning of a decade that might answer humanity's oldest question. Are we alone? Within 10 years, perhaps sooner, we will know whether TOI 700d has an atmosphere. We will know what molecules it contains. We might even know if life exists there. When the answer comes, whether it's confirmation of life or merely another lifeless world, it will change us. It will redefine our cosmic perspective. It will tell us whether Earth is unique or merely one of countless inhabited worlds. This is TOI 700d, the temperate world, an Earth-sized planet in the habitable zone of a nearby star. a place where life might exist. A reminder that the universe is vast, diverse, and full of wonders. The search continues. The observations accumulate. And soon, perhaps within our lifetimes, we will know. For this next planet, let's look at GJ 3470b and the mystery of Neptune's missing atmospheres. 96 light-years from Earth, around a faint red dwarf star, orbits a world caught in the act of transformation. GJ 3470b, a warm Neptune, larger than Earth but smaller than our solar system's ice giants, is losing its atmosphere at a catastrophic rate. Every second, millions of kilograms of hydrogen and helium escape into space, blown away by intense radiation from the nearby star. At this rate, over billions of years, GJ 3470b might lose its entire gaseous envelope, transforming from a puffy mini-Neptune into a dense rocky super-Earth. This is not a distant future. This is happening now, and by studying GJ 3470b, we are witnessing one of the most fundamental processes in planetary evolution: the transition from gaseous to rocky worlds, the creation of the mysterious Radius Valley that divides super-Earth from sub-Neptunes. The story of GJ 3470b begins with M-Earth, the M-Earth North Project, a network of small robotic telescopes designed to find transiting planets around the nearest and smallest stars. M-Earth, short for M-Dwarf Earth, was specifically designed to monitor M-Dwarf stars for transiting planets. M-Dwarfs are small, which means planets produce deeper transits relative to the star's size, making detection easier. We used 8 40-centimeter telescopes to monitor thousands of nearby M-Dwarfs every clear night, searching for the periodic dimming that indicates a transiting planet. In 2012, M-Earth detected a periodic dimming of the star GJ 3470, cataloged formally as Gliese 3470, a red dwarf in the constellation Cancer. The dimming occurred every 3.33 days with a depth of approximately 0.7%, indicating a planet roughly 4 Earth radii in size. Confirming the discovery required extensive ground-based follow-up using larger telescopes and precision instruments. We used the HARP spectrograph at La Silla Observatory in Chile to measure radial velocities, the star's wobble caused by the planet's gravity. The measurements confirmed a planetary mass of approximately 13.9 Earth masses. Combined with the radius of 4.3 Earth radii derived from transits, we calculated a density of about 0.72 grams per cubic centimeter, significantly less dense than Earth, indicating a substantial gaseous envelope. GJ 3470b was announced in 2012 as a warm Neptune, a planet intermediate in size between Earth and Neptune, with properties unlike any planet in our solar system. But this was just the beginning of the story. GJ 3470 is an M1.5 dwarf, a red dwarf star slightly larger and hotter than the smallest M dwarfs, but still much smaller and cooler than our Sun. GJ 3470 is relatively young for an M dwarf and shows moderate magnetic activity, stellar flares, chromospheric emission, X-ray radiation. This high-energy radiation is crucial for understanding GJ 3470b's atmospheric evolution. Young, active M-dwarfs produce intense UV and X-ray emission that can heat and erode planetary atmospheres through a process called photoevaporation. GJ 3470b is classified as a warm Neptune, a planet similar in size to Neptune but orbiting much closer to its star, resulting in higher temperatures. GJ 3470b is fascinating because it sits in a poorly understood size regime. It's larger than super-Earths, but smaller than Jupiter, in the sub-Neptune or mini-Neptune category that doesn't exist in our solar system. These planets are incredibly common around other stars, yet we don't fully understand how they form, what they're made of, or how their atmospheres evolve. GJ3470b's significance extends beyond its individual properties. It sits just above a critical boundary in the exoplanet size distribution, the radius valley, or Fulton gap. The radius valley is a relative scarcity of planets between about 1.5 and 2.0 Earth radii. Below this gap, we find rocky super-Earths. Above it, we find gaseous sub-Neptunes. The gap exists because of atmospheric loss. Planets that form with hydrogen-helium atmospheres either lose them entirely, dropping below the gap, or retain them, staying above the gap. GJ3470b, at 4.3 Earth radii, is well above the gap, but it's actively losing atmosphere. It's in the process of transitioning. Understanding how and why planets lose their atmospheres is crucial for understanding planetary populations, predicting which planets might be habitable, and determining the fate of worlds like GJ3470b. Almost immediately after its discovery, GJ3470b became a prime target for atmospheric characterization. Its large size, extended atmosphere, and bright host star made it ideal for transmission spectroscopy. Transmission spectroscopy works by observing the planet during transit and measuring how its atmosphere absorbs different wavelengths of starlight. GJ3470b's atmosphere is so extended, puffed up by heat, that atmospheric features are unusually strong. This makes detection easier than for denser planets with compact atmospheres. Early observations with Hubble Space Telescope's WFC-3 instrument revealed surprising results. Hubble observations in 2013 and subsequent years detected something unexpected, or rather, failed to detect what was expected. We expected to see strong water vapor absorption features in the near-infrared spectrum. Water should be abundant in a hydrogen-helium atmosphere at GJ3470b's temperature. But instead, we saw a relatively flat spectrum. The molecular features were muted, suppressed. This is a signature of high-altitude clouds or hazes that obscure the deeper atmosphere where molecules absorb light. The clouds on GJ3470b are not water clouds like on Earth. At 650 K, water exists as vapor, not liquid or ice. Instead, the clouds might be composed of photochemical hazes, complex organic molecules created when UV light breaks apart methane and other hydrocarbons, producing sooty particles that accumulate in the upper atmosphere. Photochemical hazes are common on exoplanets, particularly warm Neptunes and hot Jupiters. They form when UV radiation from the star drives chemical reactions in the upper atmosphere, creating increasingly complex molecules that condense into haze particles. These hazes scatter light broadly, muting molecular absorption features and making atmospheric characterization more difficult. We detected absorption in the helium line at 10,830 angstroms, evidence for an extended exosphere of escaping helium atoms. This was only the second time helium had been detected in an exoplanet atmosphere, and the signal was remarkably strong. The helium absorption extended well beyond the planet's optical radius, indicating that gas is escaping at high altitudes, blown away by stellar radiation. The helium detection was direct evidence of atmospheric escape, a process theorized for decades, but difficult to observe directly. By analyzing the helium signal and modeling the planet's upper atmosphere, astronomers calculated the atmospheric escape rate. Our models suggest GJ3470b is losing mass at approximately 10 to the power of 10 to 10 to the power of 11 kilograms per second. That's tens of millions to hundreds of millions of kilograms every second. Over the planet's lifetime, it might have already lost several percent of its total mass, potentially including a significant fraction of its original hydrogen-helium envelope. At this rate, GJ3470b will not lose all its atmosphere. The The planet is massive enough that even intense escape can't strip it completely over billions of years. But it might transition from a puffy mini-Neptune to a denser sub-Neptune or super-Earth, crossing the Radius Valley and joining the population of planets with thin or no hydrogen atmospheres. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spectral resolution, promised to revolutionize exoplanet atmospheric studies. GJ3470b was selected as one of JWST's early targets. GJ3470b is an ideal JWST target. The planet is large with an extended atmosphere, the host star is relatively bright, and the transit depth is significant. JWST's NIRIS and NIR spec instruments can observe transmission spectra from 0.6 to 5 microns with exquisite precision, wavelengths where water, methane, carbon dioxide, and other molecules have strong absorption features. In 2022 and 2023, JWST observed GJ3470b using multiple instruments and observing modes, obtaining the most detailed atmospheric spectrum of a sub-Neptune to date. Key JWST findings. Water vapor detection. Strong water vapor absorption features detected across multiple wavelengths, confirming water is abundant in the atmosphere despite the obscuring hazes observed at shorter wavelengths. Methane depletion. Methane absorption weaker than expected for chemical equilibrium, suggesting depletion, possibly due to photochemistry breaking apart CH4 molecules in the upper atmosphere. Carbon dioxide and carbon monoxide. Evidence for both species, providing information about carbon chemistry and atmospheric temperature structure. No strong absorption from heavy metals. Unlike some hot Jupiters, GJ3470b doesn't show strong absorption from sodium, potassium, or metal oxides, consistent with a hazy atmosphere. Extended haze layers. Spectral slope consistent with high-altitude photochemical hazes composed of complex organic molecules. JWST's observations are transformative. For the first time, we can see through the hazes to the deeper atmosphere where water vapor and other molecules exist. We can measure abundances, constrain temperature profiles, and understand the chemical processes occurring. GJ3470b is becoming one of the best characterized sub-Neptunes, a benchmark for understanding this entire class of planets. The molecules detected in GJ3470b's atmosphere tell a story about the planet's formation, evolution, and current state. The water abundance tells us about where the planet formed. If GJ3470b formed beyond the ice line in its protoplanetary disk, where water ice was abundant, and then migrated inward, we'd expect significant water enrichment. The JWST data suggest water is indeed enriched relative to a solar composition atmosphere, supporting the migration hypothesis. The methane depletion is equally telling. In a chemically equilibrated atmosphere at GJ3470b's temperature, methane should be moderately abundant. But photochemistry, driven by UV radiation from the star, breaks apart methane molecules, reducing their abundance and creating the complex organic hazes observed in the upper atmosphere. The carbon monoxide to carbon dioxide ratio, the presence or absence of other carbon-bearing molecules, the overall carbon-to-oxygen ratio. All of these constrain formation conditions and atmosphere processes. JWST is giving us the data to build comprehensive models of how sub-Neptune atmospheres behave. Like all close-orbiting planets, GJ3470b is likely tidally locked. One hemisphere permanently faces the star, the other faces eternal darkness. Tidal locking creates extreme day-night temperature contrasts on rocky planets with thin atmospheres. But GJ3470b has a thick hydrogen-helium atmosphere with low mean molecular weight, which transports heat efficiently. Our models predict strong eastward jet streams at the equator, supersonic winds flowing from the day side to the night side, redistributing heat and moderating temperature extremes. Eclipse observations, when the planet passes behind the star and we lose its thermal emission, provide information about day-side temperature and heat redistribution efficiency. Preliminary observations suggest the day side is not as hot as it would be without heat redistribution, indicating the atmosphere is efficiently transporting energy. The night side, though cooler, is probably not as cold as it would be on an airless world. Winds may reach several kilometers per second, comparable to those on hot Jupiters, but in a less extreme environment. The hazes detected in GJ 3470b's atmosphere are not static. They form, evolve, and potentially precipitate or destroyed by atmospheric dynamics. Photochemical hazes form in the upper atmosphere where UV radiation penetrates. The particles grow through coagulation, sticking together as they collide. They settle downward due to gravity, but updrafts can loft them back up. If they descend deep enough into hotter atmospheric layers, the organic molecules decompose, releasing the methane and other gases they were formed from. This creates a vertical cycle. Methane transported upward, broken apart by UV light. Haze particles form and settle, decompose at depth, methane released again. This process affects what we observe. The hazes obscure the lower atmosphere at visible wavelengths but are more transparent in the infrared, allowing JWST to probe deeper than Hubble could. The most dramatic atmospheric phenomenon on GJ 3470b is the ongoing escape, the continuous loss of gas to space. The helium exosphere extends to at least 3 planetary radii, meaning the gas cloud around GJ 3470b is enormous. Hydrogen, being lighter, escapes even more easily and extends even farther. The planet is surrounded by a vast envelope of escaping gas, visible in UV and near-UV wavelengths, creating a comet-like tail as the stellar wind sweeps the gas away. This escape is driven by multiple mechanisms. Photoevaporation, high-energy UV and X-ray radiation from the star heats the upper atmosphere to thousands of Kelvin, giving atoms enough energy to escape the planet's gravity. Stellar wind stripping. Charged particles from the stellar wind interact with the planet's upper atmosphere, accelerating escape. Hydrodynamic escape. The heated atmosphere expands outward, with gas flowing off the planet like water from a fountain. Over the next few billion years, GJ 3470b will continue losing atmosphere. Eventually, the escape rate will decline as the planet loses mass and the remaining atmosphere becomes harder to strip. The planet will shrink, become denser, and possibly transition from a mini-Neptune to a super-Earth or sub-Neptune with a very different appearance and properties. GJ 3470b is one of thousands of sub-Neptunes and mini-Neptunes discovered around other stars. Understanding this one planet helps us understand them all. Sub-Neptunes are the most common type of planet in the galaxy based on Kepler statistics, yet they're poorly understood because we have nothing like them in our solar system. They're too large to be rocky like Earth and too small to be gas giants like Jupiter. GJ 3470b, being nearby, bright, and well-characterized, serves as a Rosetta Stone for understanding sub-Neptunes everywhere. Key questions GJ 3470b helps answer. What are sub-Neptunes made of? GJ 3470b's density suggests a rocky or icy core comprising most of the mass, surrounded by a substantial hydrogen-helium envelope comprising 5 to 20% of the total mass. How do sub-Neptunes lose their atmospheres? GJ 3470b demonstrates photoevaporation in action, showing that intense stellar radiation can drive significant mass loss. Why do some planets retain atmospheres while others lose them? GJ 3470b's properties, its mass, distance from the star, host star age, and activity, help calibrate models predicting which planets will evolve into which outcomes. Can sub-Neptunes have habitable conditions? GJ 3470b itself is too hot and gas-dominated for habitability, but understanding atmospheric retention informs the search for habitable planets around M dwarfs. GJ 3470b's atmospheric composition provides clues about where and how it formed. The water enrichment suggests GJ 3470b formed beyond the ice line, the distance in the protoplanetary disk where water ice could condense, roughly 1 to 2 AU for an M dwarf. The planet accreted ice-rich planetesimals, built a core massive enough to capture gas from the disk, then migrated inward to its current location at 0.0355 AU. The migration could have been smooth through disk interactions, or more violent through gravitational scattering with other planets. The current circular orbits suggest smooth migration rather than violent scattering. Tidal forces from the star have circularized any initial eccentricity and locked the planet's rotation to its orbit. GJ 3470b is not unique, but it is uniquely well studied. Comparing it to similar planets reveals patterns. By comparing planets across different sizes, stellar hosts, and irradiation levels, we're mapping out the diversity of sub-Neptunes. Some have clear atmospheres, some have hazes, some are losing mass rapidly, others slowly. GJ 3470b, with its combination of active escape, detectable molecules, and extended atmosphere, occupies a unique position that helps us calibrate our understanding of the entire population. GJ 3470b remains a high-priority target for continued observations with multiple facilities, planned and ongoing studies, JWST extended observations, additional transits and eclipses with different instruments to refine atmospheric composition, search for additional molecules, and measure temporal variability. High-resolution ground-based spectroscopy. Using extremely large telescopes and instruments like espresso to detect individual atomic and molecular lines, measure wind velocities, and probe three-dimensional atmospheric structure. UV observations of atmospheric escape. Continued monitoring with Hubble and future UV missions to track how escape rates change with stellar activity and over time. Phase curve observations. Monitoring the planet's brightness as it orbits to map temperature distribution, search for weather patterns, and constrain heat redistribution efficiency. Every observation refines our understanding. Each transit reveals new details about the atmosphere. Each eclipse constrains temperature structure. Over the coming decade, GJ 3470b will be one of the most intensively studied exoplanets, and what we learn will inform thousands of other discoveries. GJ 3470b represents both what we can achieve now and what future missions will accomplish for even more challenging targets. Future capabilities. Atmospheric Remote Sensing Infrared Exoplanet Large Survey. ESA mission launching 2029 will survey 1000 plus exoplanet atmospheres, including detailed studies of sub-Neptunes like GJ 3470b. Extremely large telescopes, 30 to 40 meter ground-based telescopes, achieving spectroscopic resolution and sensitivity far beyond current capabilities. Habitable Worlds Observatory, proposed NASA flagship mission for direct imaging and characterization of potentially habitable planets. GJ 3470b shows us what's possible. We've gone from detecting the planet's existence to measuring its mass and radius, to detecting molecules in its atmosphere, to understanding its atmospheric chemistry and dynamics, to observing its evolution in real time. Future missions will do this for smaller, cooler, potentially habitable planets, the ultimate goal of exoplanet science. Imagine approaching GJ 3470b. From a distance, it appears as a pale blue-purple sphere, slightly larger than Neptune, bathed in the red-orange glow of its M-dwarf star. But as you draw closer, you notice something unusual. The planet is surrounded by an enormous, diffuse cloud of gas, extending far beyond the solid planet, glowing faintly in UV light. You enter the exosphere, tenuous gas, mostly hydrogen and helium, heated to thousands of degrees by stellar radiation. The gas flows outward, escaping to space at millions of kilograms per second. You are passing through the edge of a world that is slowly evaporating. Descending deeper, you encounter the haze layer, thick organic particles suspended in the upper atmosphere, products of photochemistry, giving the planet a hazy, featureless appearance from outside. The sky here would be a murky brown-orange, the star a diffuse glow through the haze. Below the hazes, the atmosphere clears slightly. You are now in the hydrogen-helium envelope where water vapor, methane, and other molecules exist as gases. The temperature rises as pressure increases. The atmosphere is thick, heavy, rushing with powerful winds. Lightning might arc through clouds of exotic composition. Ammonium hydrosulfide, water ice crystals at certain altitudes. Deeper still, at pressures hundreds of times Earth's surface, the hydrogen transitions from gas to supercritical fluid, neither clearly gaseous nor liquid. And somewhere below, perhaps hundreds or thousands of kilometers down, lies the core, rock and ice compressed to exotic states, the solid foundation of this gas-shrouded world. GJ 3470b is 96 light-years away. We will never visit it. We will never send a probe through its atmosphere or sample its gases directly. But through the light it blocks, the radiation it absorbs, the shadow it casts, we have learned more about this world than we know about some planets in our own solar system. We know its size and mass. We know it's losing its atmosphere. We know what molecules fill its air and what hazes obscure its upper regions. We know how it formed, how it migrated, how it's evolving. We understand its weather, its chemistry, its fate. GJ 3470b is more than one planet. It's a laboratory for understanding how worlds evolve, how atmospheres respond to stellar radiation, how the diversity of planetary systems arises. It's a preview of transitions happening throughout the galaxy. Mini Neptunes transforming into super-Earths, gaseous worlds becoming rocky ones, the sculpting of planetary populations by stellar energy. This is GJ 3470b, the evaporating world, a warm Neptune losing its atmosphere, a planet caught between two states, gaseous and rocky, temporary and transitional. A reminder that planets are not static. They evolve, they change, and by watching them change, we understand the forces that shape all worlds, including our own. The observations continue. The atmosphere escapes, and the universe always teaches us more than we expected. Earth is all right, but what if it could get even better? It just might with HD 97658b. In the search for super-Earth atmospheres. For 3 years, a planet had been hiding in plain sight. HD 97658b was discovered in 2008 through radial velocity measurements. The star's wobble revealing an unseen companion. Astronomers knew the planet existed, knew its mass and orbital period, but they didn't know its size. In 2011, while analyzing Kepler data, astronomer Andrew Howard noticed something subtle, a faint, periodic dimming of HD 97658 every 9.5 days. The planet was transiting. For the first time, we could measure its radius, calculate its density, and begin to understand what kind of world it truly was. The transit depth was small, only about 0.04%, at the very edge of Kepler's detection capabilities. But it was there, and it told a story astronomers had been eager to hear. HD 97658b was not a gas giant. It was a super-Earth, straddling the boundary between rocky planets and small Neptunes, a world unlike any in our solar system. The story of HD 97658b begins with the Eta-Earth survey, a systematic radial velocity campaign using the Keck telescope to search for low-mass planets around nearby Sun-like stars. The Eta-Earth survey aimed to answer a fundamental question: how common are Earth-mass planets around Sun-like stars? We monitored over 200 nearby stars with extreme precision, measuring their radial velocities, tiny wobbles caused by orbiting planets. HD 97658 was among our targets, and in 2008, we detected a clear periodic signal with a 9.5-day period. The radial velocity amplitude, the speed of the star's wobble, was approximately 2.8 meters per second. This revealed the planet's minimum mass, at least 7.5 Earth masses, potentially more depending on the orbital inclination. Radial velocity tells us a planet exists and gives us its mass, but it leaves critical questions unanswered. What is the planet's true mass? What is its size? What is it made of? For these answers, we need transits. We need to see the planet cross in front of its star. When Kepler launched in 2009, it observed a fixed field of view containing about 150,000 stars. By chance, HD 97658 was in that field. We knew HD 97658b existed from our radial velocity measurements. If the orbit happened to be aligned edge-on from our perspective, the planet would transit. The probability was about 10%, long odds but worth checking. When Kepler data became available in 2010, I started searching for transits. Finding the transit was not straightforward. The transit depth was minuscule, about 0.04%, meaning the planet blocks only 0.04% of the star's light. Stellar variability, instrumental noise, and cosmic rays created variations larger than the transit signal. Sophisticated algorithms and multiple transits were needed to confirm the detection. After carefully analyzing 3 years of Kepler data and detecting multiple transits spaced precisely 9.5 days apart, we confirmed it. HD 97658b transits. This was significant because it was one of the first planets discovered by radial velocity that was later found to transit, allowing us to measure both mass and radius, the keys to understanding composition. HD 97658 is what we call a solar analog, close enough to the Sun in mass, temperature, and age that planets around it experience similar stellar environments. It's older than the Sun, which means it's had more time to settle into stable behavior. And crucially, at magnitude 7.7, it's one of the brightest stars known to host a transiting super-Earth, making detailed atmospheric studies possible. With both mass and radius measured, astronomers could calculate HD 97658b's density, and the result was surprising. HD 97658b's density of 3.44 g/cm superscript 3 tells us this planet cannot be purely rocky like Earth. A pure rock-iron composition would give a density closer to 5 to 6 g/cm superscript 3. The lower density means HD 97658b must have a significant volatile component, either water ice, a gaseous envelope, or both. At 2.25 Earth radii, it sits right at the radius valley boundary, making it a critical test case for understanding the transition from rocky super-Earths to gaseous sub-Neptunes. The radius valley, or Fulton Gap, a scarcity of planets between approximately 1.5 and 2.0 Earth radii, represents a fundamental divide in planetary types. Below the radius valley, we find rocky super-Earths, scaled-up versions of Earth and Venus. Above it, we find sub-Neptunes with substantial hydrogen-helium atmospheres. HD 97658b, at 2.25 Earth radii, sits just above this transition. It likely has a rocky core, but also a significant gaseous envelope, perhaps 1 to 5% of its mass as hydrogen and helium. Understanding planets like this tells us how atmospheres are retained or lost, and where the boundary between rocky and gaseous really lies. With HD 97658b's bright host star and favorable geometry, astronomers recognized it as an excellent target for atmospheric characterization, detecting what gases exist in the planet's atmosphere by analyzing how starlight filters through it during transits. Transmission spectroscopy measures the planet's apparent size at different wavelengths. If molecules in the atmosphere absorb certain colors of light, the planet appears slightly larger at those wavelengths. For HD 97658b, the brightness of the host star and the planet's extended atmosphere, puffed up by heat, made detection of atmospheric features plausible even with pre-JWST facilities. Hubble Space Telescope's Wide Field Camera 3 and Space Telescope Imaging Spectrograph conducted transmission spectroscopy observations of HD 97658b, probing the atmosphere in the near-infrared and visible wavelengths. Key Hubble findings: water vapor detection. Tentative evidence for water vapor absorption features in the 1.1 to 1.7 micron range, though the signal was not definitive due to contamination from stellar activity. High-altitude clouds or hazes. The spectrum showed muting of molecular features, consistent with clouds or hazes obscuring the deeper atmosphere, a common problem in atmospheric characterization of subneptunes. Sodium and potassium. Weak or absent features where strong absorption was expected, further suggesting high-altitude aerosols blocking the view. The Hubble data suggested HD 97658b has an atmosphere. The planet is not just a bare rock, but the atmosphere is partially obscured by clouds or hazes. This is frustrating, but scientifically interesting. The clouds tell us about atmospheric chemistry and dynamics. Understanding why some planets have cloudy atmospheres and others don't is key to decoding atmospheric diversity. At HD 97658b's temperature, 740 to 780 K, several types of clouds could exist. At these temperatures, we expect clouds composed of refractory materials, substances that remain solid or liquid at high temperatures. Possibilities include silicate clouds, particles of vaporized rock that condense into tiny droplets, similar to lava droplets. Or we might have photochemical hazes, complex organic molecules created when UV light breaks apart hydrocarbons like methane, producing sooty particles that accumulate high in the atmosphere, similar to what we see on Titan. These clouds have profound effects on the planet's energy balance and observability. They reflect sunlight, keeping the planet cooler than it would otherwise be, and they obscure the deeper atmosphere, making it difficult to detect molecular features that would tell us the atmospheric composition. While transit observations probe the planet's atmosphere as starlight filters through it, eclipse observations detect thermal emission from the planet's dayside. During secondary eclipse, we lose the planet's light as it passes behind the star. By comparing the system brightness with and without the planet visible, we measure how much light the planet itself emits or reflects. For HD 97658b, Spitzer's infrared observations at 4.5 microns detected the planet's thermal emission, giving us information about dayside temperature and heat redistribution. The Spitzer data suggested a dayside temperature consistent with models, indicating moderate heat redistribution from day to night. Not as efficient as hot Jupiter's, but better than expected for a planet with this mass and size. The James Webb Space Telescope, with sensitivity far exceeding Hubble and coverage extending into the mid-infrared, opened new possibilities for characterizing planets like HD 97658b. JWST is optimized for exactly the kind of science HD 97658b demands. Its infrared instruments, NIR-SPEC, NIRIS, MIRI, can detect molecules that Hubble couldn't, penetrate clouds more effectively and achieve signal-to-noise ratios that reveal subtle atmospheric features. For bright stars like HD 97658, JWST can obtain transmission spectra of unprecedented quality. HD 97658b was observed by JWST as part of multiple programs aimed at characterizing super-Earth and sub-Neptune atmospheres. The results provided the most detailed view yet of this transitional world. JWST key findings: water vapor confirmation, strong, definitive detection of water vapor across multiple wavelengths, confirming previous tentative Hubble detections. Water is a major atmospheric constituent. Carbon dioxide detection, clear absorption feature at 4.3 microns, indicating carbon dioxide in the atmosphere. The first time CO2 had been definitively detected in a planet this small. Methane depletion or absence. Expected methane features were weak or absent, suggesting photochemical destruction of methane high in the atmosphere. Sulfur dioxide. Possible evidence for sulfur-bearing compounds, though less certain than for larger planets like WASP 39b. Persistent cloud/haze layer. Even with JWST's capabilities, evidence for high-altitude clouds or hazes remained, muting some spectral features. The JWST data for HD 97658b are transformative. We now have definitive detections of water vapor and carbon dioxide, key molecules for understanding atmospheric composition and chemistry. The carbon-to-oxygen ratio, the presence or absence of methane, the persistence of clouds, all of these constrain how the planet formed, what it's made of, and how its atmosphere behaves. Each molecule detected in HD 97658b's atmosphere provides clues about the planet's history and current state. Water vapor enrichment suggests HD 97658b formed beyond the ice line in its protoplanetary disk, where water ice was abundant and migrated inward. Carbon dioxide tells us about carbon chemistry and atmospheric processing. The absence or depletion of methane, which should be in chemical equilibrium at these temperatures, indicates photochemistry is actively breaking apart methane molecules, creating the hazes we observe. The carbon-to-oxygen ratio, derived from abundances of carbon dioxide, carbon monoxide, water, and other molecules, provides insights into where and how the planet accreted material. If HD 97658b formed close to the star, we'd expect a carbon-to-oxygen ratio similar to the host star. But if it formed farther out and accreted ice-rich material, the Karov ratio would be different. JWST data are giving us the precision to calculate this ratio and test formation theories. Like most close-orbiting planets, HD 97658b is likely tidally locked. One hemisphere permanently faces the star, the other faces eternal night. Tidal locking creates day-night temperature contrasts that drive atmospheric circulation. For HD 97658b, with its substantial atmosphere and moderate mass, we expect strong equatorial jet streams flowing from dayside to nightside at speeds potentially reaching several kilometers per second, supersonic winds that redistribute heat in moderate temperature extremes. The efficiency of heat redistribution depends on atmospheric composition, mass, and the planet's rotation state. Eclipse observations and phase curves, monitoring the planet's brightness throughout its orbit, provide data to test these models. If heat redistribution is efficient, the night side would be relatively warm and the day-night temperature contrast modest. If inefficient, the night side would be much colder, possibly cold enough for atmospheric gases to condense into ices. For HD 97658b, Spitzer and JWST eclipse data suggest moderate redistribution. Not as efficient as hot Jupiter's, but better than expected for a planet this size. The clouds detected in HD 97658b's atmosphere are not static. They form, evolve, and dissipate based on temperature, pressure, and atmospheric dynamics. In HD 97658b's atmosphere, clouds might form through multiple mechanisms. Silicate clouds form when rock vapor, silicon, iron, magnesium, condenses into tiny droplets as gas rises and cools. These form at specific temperature-pressure levels. Above them, photochemical hazes form when UV radiation breaks apart methane and other hydrocarbons, creating complex organic molecules that condense into sooty particles. These hazes can extend to very high altitudes. These cloud particles horizontally and vertically. On the hot day side, silicates might remain vaporized. On the cooler night side, they condense into clouds and rain out, literally raining molten rock or metal droplets. Updrafts transport vapor back to the day side, continuing the cycle. One of the key questions about HD 97658b is atmospheric retention. Can it keep its atmosphere over billions of years, or will it slowly lose gas to space? HD 97658b orbits close enough to its star that it receives significant UV and X-ray radiation, which heats the upper atmosphere and drives atmospheric escape through photoevaporation. However, the planet is massive enough, nearly 8 Earth masses, that its gravity is strong enough to retain most of its atmosphere. Our models suggest HD 97658b is stable against runaway atmospheric loss, though it's probably losing some gas slowly over billions of years. The balance between atmospheric heating and gravitational retention determines the planet's long-term fate. HD 97658b sits near the boundary, massive enough to retain an atmosphere, but light enough that escape is ongoing. Over billions of years, it might lose a few % of its atmospheric mass, shrinking slightly, but remaining fundamentally a sub-Neptune rather than transforming into a bare super-Earth. Can super-Earths be habitable? HD 97658b itself is far too hot for habitability. With temperatures around 750 K, water exists only as vapor, and the planet lacks a solid or liquid surface accessible to life as we know it. But studying HD 97658b informs the search for habitable worlds. Every super-Earth or sub-Neptune we characterize teaches us about atmospheric retention, composition, and evolution. HD 97658b shows that planets of this size can retain substantial atmospheres. It demonstrates that we can detect and characterize those atmospheres with current technology, and it helps us understand the transition between rocky and gaseous world. The detection of water vapor on HD 97658b confirms that water, essential for life as we know it, exists on planets beyond Earth. But the form matters. On HD 97658b, water exists as high-temperature vapor mixed into a hydrogen-helium atmosphere. There's no liquid water ocean, no accessible surface where prebiotic chemistry could occur. But the mere presence of water and the ability to detect it spectroscopically is encouraging. When we observe cooler super-Earths in habitable zones, we'll use the same techniques, and those planets might have liquid water on solid surfaces, conditions compatible with life. HD 97658b is one of hundreds of super-Earths and sub-Neptunes discovered around nearby stars. Each one adds to our understanding of this diverse population. Super-Earths and sub-Neptunes are the most common planetary type in the galaxy, yet they don't exist in our solar system. They span a huge range of properties, masses from 2 to 20 Earth masses, radii from 1.2 to 4 Earth radii, compositions from rocky to gaseous. HD 97658b, with detailed radial velocity, transit, and atmospheric characterization, is a benchmark, one of the best understood planets in this category. How do planets like HD 97658b form? And why are they so common around other stars but absent from our solar system? There are multiple formation pathways. Some super-Earths might form in situ, growing from the protoplanetary disk material at their current locations. Others, like HD 97658b with its water enrichment, probably formed farther out beyond the ice line, accreted ice and gas, then migrated inward through interactions with the disk or other planets. The composition and atmospheric properties constrain which pathway is most likely. The absence of super-Earths in our solar system might be explained by Jupiter's early formation and migration, which prevented the growth of super-Earths in the inner solar system. Or it might be statistical chance. Our system happens to lack them, but they're common elsewhere. HD 97658b and planets like it are paving the way for even more detailed atmospheric studies with future facilities. Upcoming capabilities. JWST Extended Mission. Additional observations of HD 97658b and similar planets to search for temporal variability, detect minor atmospheric constituents, and refine atmospheric models. Extremely large telescopes. Ground-based 30 to 40-meter telescopes will achieve high-resolution spectroscopy, detecting individual molecular lines, measuring wind velocities, and probing three-dimensional atmospheric structure. Atmospheric Remote Sensing Infrared Exoplanet Large Survey. ESA mission launching 2029 will survey 1,000 plus exoplanet atmospheres, including comprehensive studies of super-Earths and subneptunes. Proposed NASA flagship mission for direct imaging and spectroscopy of potentially habitable planets. Each generation of instruments reveals new details. HD 97658b went from a radial velocity detection to a transiting planet to a world with a characterized atmosphere. Future observations will measure isotope ratios, detect trace species, map atmospheric circulation in 3 dimensions. And the techniques we develop on planets like HD 97658b will be applied when we study truly habitable worlds. Imagine standing, if you could, somewhere above HD 97658b, looking down at this transitional world. You would see a planet slightly more than twice Earth size, shrouded in thick clouds that obscure the surface, if there's a surface to see. As you descended through the atmosphere, you would pass first through the haze layers, photochemical particles suspended in the thin upper atmosphere, products of ultraviolet chemistry. The sky would be murky, the star a diffuse glow. Deeper, you would enter the silicate cloud layers where vaporized rock condenses into droplets. The temperature would rise, the pressure increase. The atmosphere would become denser, heavier with hydrogen and helium, laced with water vapor and carbon dioxide. How deep could you go? Thousands of kilometers down, the atmosphere would transition from gas to supercritical fluid, neither clearly gaseous nor liquid. And somewhere below, perhaps, lies a core of rock and ice, compressed by the enormous weight of the atmosphere above. Or perhaps there is no solid surface, just atmosphere all the way down, gradually becoming denser until it transitions to exotic states of matter we can barely imagine. HD 97658b is 69.5 light-years away, close by cosmic standards, but far beyond our reach. We will never visit it. We will never send a probe to sample its atmosphere or measure its properties directly. But through the light it blocks, the radiation it absorbs, the transits and eclipses we observe, we have learned more about this world than seemed possible just decades ago. We know its mass and size. We know it has an atmosphere rich in water vapor and carbon dioxide. We know clouds obscure its upper layers. We know it's losing atmosphere slowly, but retaining most of it. We understand its formation, migration, and evolution. HD 97658b is more than one planet. It's a representative, one of countless super-Earths and sub-Neptunes throughout the galaxy. It's a bridge between rocky and gaseous worlds, showing us how planets transition across that boundary. It's a laboratory for atmospheric science, teaching us to read the chemical signatures of distant atmospheres. This is HD 97658b, the transitional world, a super-Earth with a substantial atmosphere, a planet that is neither fully rocky nor fully gaseous, but something in between. A reminder that the universe contains more variety than we imagined, that planets come in configurations we never predicted, and that understanding them requires patience, ingenuity, and the determination to keep looking, keep observing, keep learning. The observations continue. The atmosphere reveals its secrets, and with each new discovery, we understand a little more about the incredible diversity of worlds that populate our galaxy. Things are about to get big with this next world. HAT P32b, the inflated giant, the puzzle of bloated hot Jupiters, a planet that shouldn't exist. 1,000 light-years from Earth, in the constellation Andromeda, orbits a planet that defies our understanding of planetary physics. HAT P32b, a gas giant nearly twice Jupiter's size, yet only as massive as Jupiter itself. A density so low it would float in water. A world heated to over 1,900 Kelvin, hot enough that iron exists as vapor in its atmosphere. This is an inflated hot Jupiter, a planetary paradox. By all accounts, HAT P32b should have collapsed under its own gravity billions of years ago. It remains impossibly puffy, swollen by processes we're only beginning to understand. HAT P32b is not alone. Dozens of hot Jupiters show similar inflation, but few are as extreme. Studying this world helps us understand one of the most puzzling phenomena in exoplanet science. Why do some gas giants puff up to impossible sizes? The Hungarian-made Automated Telescope Network, HATNet, began operations in 2003 with a straightforward goal: find transiting exoplanets around bright stars by monitoring hundreds of thousands of stars every clear night. HATNet uses small, wide-field telescopes, only 11 centimeters in aperture, to monitor large swaths of sky simultaneously. We're not looking for faint stars far away. We're looking for nearby, bright stars where planets produce deep transits easy to detect and follow up. HAT P32 was discovered in 2011 during our survey of the Andromeda constellation. In December 2010, HATNet detected periodic dimming of the star HAT P32, a bright F-type star showing transits every 2.15 days with a depth of approximately 1.8%. The signal was clear and regular, indicating a large planet in a very close orbit. Confirming HAT P32b required extensive ground-based follow-up using larger telescopes and precision instruments. We used the Tillinghast reflector at Fred Lawrence Whipple Observatory and the Keck telescope in Hawaii to obtain high-resolution spectra and radial velocity measurements. The radial velocity amplitude, about 100 meters per second, confirmed a planetary mass of approximately 0.94 Jupiter masses. Combined with the radius derived from transits, approximately 1.79 Jupiter radii, we calculated an extremely low density of just 0.17 grams per cubic centimeter. For comparison, Jupiter has a density of 1.33 g/cm superscript 3. Saturn, the least dense planet in our solar system, has a density of 0.69 g/cm superscript 3. HAT P32b at 0.17 g/cm superscript 3 is less than 1/8 Saturn's density. roughly the density of balsa wood, far less dense than water. This was immediately interesting. Hot Jupiters are known to be inflated, heated by intense stellar radiation. Their atmospheres puff up. But HAT P32b was among the most inflated ever discovered. Something was preventing this planet from contracting under its own gravity and understanding what became a key research priority. HAT P32 is not a typical star, and its unusual properties significantly affect its planet. HAT P32 is unusual in several ways. It's hotter than the Sun, more massive, and, critically, it rotates extremely rapidly. A rotation period of 2.8 days means the star spins more than 10 times faster than the Sun. This rapid rotation generates a strong magnetic field and high activity levels. The star shows significant star spots, flares, and magnetic variability. The rapid rotation has profound implications for the planet. Tidal interactions between the planet and the rapidly rotating star transfer energy into the planet's orbit and interior, potentially contributing to the extreme inflation. In 2012, astronomers made an intriguing discovery using the Rossiter-McLaughlin effect, a spectroscopic technique that reveals how a planet's orbit is aligned with its star's rotation. During transit, the planet blocks different parts of the star's rotating surface. If the orbit is aligned with the star's equator, the planet blocks the star's blue-shifted approaching side first, then the red-shifted receding side. This creates a characteristic pattern in the star's radial velocity. For HAT P32b, we found something different. The orbit is significantly misaligned with the star's spin axis. The spin-orbit misalignment angle, called the obliquity, is approximately 85 degrees for HAT P32b. This means the planet's orbit is nearly perpendicular to the star's rotation, suggesting a violent migration history involving gravitational scattering with other planets or stellar companions. Misaligned orbits tell us these planets didn't form where we find them through gentle disk migration. Instead, they were likely scattered inward through chaotic gravitational interactions, planet-planet scattering, or quasi-litive cycles with a distant stellar companion. HAT P32b's extreme misalignment is evidence of a tumultuous past. HAT P32b exemplifies the hot Jupiter class, gas giants orbiting extremely close to their stars, heated to extreme temperatures. HAT P32b is remarkable for its extreme inflation. With a radius nearly 1.8 times Jupiter's, it's one of the largest hot Jupiters known. The planet receives enormous stellar radiation, about 2,000 times what Earth receives from the Sun. This intense heating should puff up the atmosphere, but the degree of inflation observed exceeds what standard models predict. Something additional is energizing the planet's interior. Hot Jupiter inflation has puzzled astronomers since the first discoveries. Multiple mechanisms have been proposed, but none fully explains the most extreme cases like HAT P32b. Proposed inflation mechanisms. 1. Ohmic dissipation. Electrical currents induced by the planet's magnetic field interacting with atmospheric winds generate heat deep in the interior, preventing contraction. 2. Kinetic energy deposition. Breaking atmospheric waves or subsonic winds deposit kinetic energy into the deep interior, heating it from within. 3. Enhanced opacity. Certain atmospheric constituents, titanium oxide, vanadium oxide, or other species, increase opacity to thermal radiation, trapping heat more efficiently. 4. Tidal heating. For eccentric orbits, like HAT P32b's, tidal flexing as the planet's distance from the star varies generates internal heating through friction. 5. Stellar irradiation. Intense stellar radiation heats the upper atmosphere, which somehow transports energy deep into the interior. For HAT P32b, Tidal heating is particularly interesting because of the planet's eccentric orbit. Even a small eccentricity, 0.163 for hat, P32b, means the planet's distance from the star varies by about 20% during each orbit. This causes tidal flexing, squeezing, and stretching the planet, generating heat through friction in the interior. Combined with ohmic dissipation from the strong stellar magnetic field interacting with atmospheric winds, we might explain the extreme inflation. At 1,900 K, hat P32b is hot enough that most molecules dissociate into atoms. Iron, magnesium, titanium exist as free atoms or ions. Complex molecules cannot survive. Like all close-orbiting planets, hat P32b is likely tidally locked. One hemisphere permanently faces the star, the other faces darkness. On hat P32b's day side, temperatures might reach 2,200 to 2,400 K, hot enough that the planet glows with its own visible light, appearing deep red to orange. The night side, receiving no direct starlight, cools to perhaps 1,400 to 1,600 K. Supersonic winds, potentially reaching 5 to 10 kilometers per second, flow from the hot day side to the cooler night side, redistributing heat. Eclipse observations. When a planet passes behind the star and we lose its thermal emission, provide direct measurements of the dayside temperature and heat redistribution efficiency. Hat P32b's large size, high temperature, and bright host star make it an excellent target for atmospheric characterization through transmission spectroscopy. Transmission spectroscopy works by measuring the planet's apparent size at different wavelengths during transit. Molecules in the atmosphere absorb specific wavelengths, making the planet appear larger at those colors. For hat P32b, the extended, inflated atmosphere creates strong signals easier to detect than for denser planets. Early ground-based and Hubble observations detected strong absorption features from sodium and potassium, alkali metals that exist as free atoms at hat P32b's temperatures. Sodium and potassium have strong absorption lines in the optical spectrum, the famous sodium D lines that give street lamps their yellow-orange color. On hat P32b, we detected these features clearly, confirming that sodium and potassium exist as atomic vapor in the upper atmosphere. The strength and shape of the absorption tell us about atmospheric temperature, pressure, and the presence or absence of clouds. Unlike some hot Jupiters where clouds obscure these features, hat P32b shows relatively clear atmospheric signatures, evidence that high temperatures have vaporized most cloud-forming species or kept them at lower altitudes. Hubble's Wide Field Camera 3, observing in the near-infrared, detected evidence for water vapor despite the planet's extreme temperatures. Key atmospheric constituents. Water vapor, H2O. Despite temperatures exceeding 1,900 K, some water survives as vapor. The abundance is lower than expected for solar composition, possibly indicating depletion through photodissociation or sequestration at depth. Hydrogen, H2, and helium, He, dominant atmospheric constituents comprising most of the mass, not directly detectable in transmission, but inferred from mean molecular weight. Sodium, Na, and potassium, K, strong detections, existing as free atoms in the hot upper atmosphere. Titanium oxide, TO, and vanadium oxide, VO, possible presence, though observations are inconclusive. These molecules can create temperature inversions by absorbing stellar radiation high in the atmosphere. Iron, Fe, and magnesium, Mg, expected to exist as atomic vapor at these temperatures, though direct detections are challenging. The atmospheric composition tells us about the planet's formation and current state. Water vapor depletion suggests photodissociation. UV radiation breaks apart water molecules in the upper atmosphere, with hydrogen escaping to space and oxygen potentially reacting with other species. The presence of alkali metals at high altitudes indicates a relatively clear atmosphere without extensive hazes, at least in some spectral regions. One of the key questions about hot Jupiter atmospheres is whether they exhibit temperature inversions, layers where temperature increases with altitude rather than decreasing. Temperature inversions are created when molecules like titanium oxide or vanadium oxide absorb stellar radiation high in the atmosphere, heating that layer. HAT P32b shows tentative evidence for a temperature inversion based on eclipse spectroscopy. The emission spectrum suggests the upper atmosphere is hotter than the layer below, but the evidence is not conclusive. More observations, particularly with JWST, are needed to confirm the inversion and identify which molecules cause it. HAT P32b's atmosphere is in constant, violent motion, driven by the extreme day-night temperature contrast. Our three-dimensional circulation models predict eastward equatorial jet streams reaching 5 to 10 kilometers per second, well above the speed of sound in the atmosphere. These jets transport heat from the day side to the night side. The hottest point on the planet is not directly under the star, but offset eastward by the wind flow, a phenomenon we've observed on many hot Jupiters. The winds are so powerful they dominate atmospheric chemistry. Species that would normally condense into clouds on the night side are swept back to the day side before they can settle. The atmosphere is in perpetual circulation, preventing the establishment of static weather patterns. At HAT P32b's extreme temperature and low surface gravity, atmospheric escape is inevitable. At P32b's upper atmosphere is heated to thousands of Kelvin by stellar UV and X-ray radiation. The planet's low surface gravity, only 30% of Jupiter's due to the inflated radius, means the escape velocity is lower, making it easier for atmospheric particles to reach escape velocity and leave the planet. We expect HAT P32b is losing hydrogen, helium, and potentially heavier species like metals at rates of millions of kilograms per second. Over the planet's lifetime, billions of years, this mass loss might remove a significant fraction of the atmosphere, though the planet is massive enough that total atmospheric loss is unlikely. More critically, mass loss affects atmospheric composition, preferentially removing lighter elements and potentially enriching the atmosphere in heavier species. HAT P32b likely generates a strong magnetic field through dynamo action in its metallic hydrogen interior. This field interacts with atmospheric winds and the stellar magnetic field in complex ways. The magnetic field affects atmospheric dynamics, creating regions of enhanced or suppressed convection. Interactions between the planet's magnetic field and the stellar magnetic field might generate intense electrical currents, auroras, and possibly lightning storms far more powerful than anything on Jupiter. The ohmic heating from these currents could be a significant energy source, contributing to the planet's inflation. HAT P32b is one of over 400 known hot Jupiters. Yet even within this diverse population, it stands out for its extreme properties. Hot Jupiters span a huge range of properties. Masses from 0.1 to 10 Jupiter masses, radii from 0.7 to 2.0 Jupiter radii, temperatures from 1,000 to 3,000 K. HAT P32b sits at the extreme end of the inflation spectrum. Studying planets like this helps us understand the upper limits of planetary inflation and what physical processes drive these extremes. Each hot Jupiter teaches us something different. HAT P32b specifically illuminates how tidal heating, stellar rotation, and orbital eccentricity contribute to inflation. HAT P32b did not form where we find it. Giant planets cannot form this close to their stars. There isn't enough material, and temperatures are too high for ice and gas to accumulate. Hat P32b formed in the outer protoplanetary disk, several AU from the star where temperatures allowed ice to condense and gas to accumulate. After forming, it migrated inward. The highly misaligned orbit and moderate eccentricity suggest violent migration. Likely planet-planet scattering, where gravitational interactions with another planet ejected one planet and sent Hat P32b plunging toward the star on an eccentric, misaligned orbit. Over time, tidal forces from the star gradually circularize the orbit, but the process is not yet complete. Hence the remaining eccentricity of 0.163. The misalignment persists because realigning the orbit through tidal forces would take far longer than the age of the system. The James Webb Space Telescope promises to revolutionize our understanding of Hat P32b and hot Jupiters like it. JWST's infrared instruments, NIR-SPEC, NIRIS, MIRI, can detect molecules that were beyond Hubble's reach. For Hat P32b, we're looking for carbon monoxide, carbon dioxide, methane, if any survives, additional water features, and potentially exotic species like CO, metal hydrides, or free metals in the upper atmosphere. Eclipse spectroscopy will definitively determine if a temperature inversion exists and which molecules cause it. Phase curve observations, monitoring the planet's brightness throughout its orbit, will map three-dimensional temperature structure, track the hotspot movement, and constrain heat redistribution efficiency with unprecedented precision. Ground-based, extremely large telescopes with adaptive optics and high-resolution spectrographs will complement JWST's observations. High-resolution spectroscopy, is almost equal to 100,000, can resolve individual molecular lines Doppler shifted by atmospheric winds. For Hat P32b, we can measure wind velocities directly, detect vertical atmospheric motion, map the three-dimensional wind field, and potentially detect the planet's magnetic field through Zeeman splitting of spectral lines. These observations reveal atmospheric dynamics in detail impossible with lower-resolution spectroscopy. Long-term monitoring of Hat P32b can reveal subtle changes in the orbit that constrain tidal interactions and search for additional planets. By measuring transit times over many years, we can detect orbital decay, the planet spiraling inward due to tidal friction, or transit timing variations caused by gravitational perturbations from unseen planets. For Hat P32b, with its rapid stellar rotation and close orbit, tidal evolution should be detectable over decades of observation. Imagine approaching Hat P32b from interstellar space. At first, you might mistake it for a star. It glows faintly orange-red from its own heat, a world radiating the energy it absorbs from its nearby sun. As you draw closer, the planet's immense size becomes apparent. Nearly twice Jupiter's radius, yet somehow less massive. You're witnessing one of the most inflated worlds in the galaxy, a planet swollen to impossible proportions by processes we're still struggling to understand. The star dominates the sky, brilliant white, 30 times larger in apparent size than our Sun appears from Earth. Every 2.15 days, the planet completes another orbit, locked in gravitational embrace with its rapidly spinning star. Descending toward the planet, you encounter the extended upper atmosphere, tenuous gas heated to thousands of degrees, streaming away into space. The atmosphere here is not air, but a plasma of ionized hydrogen and helium, laced with vaporized metals, iron, magnesium, sodium, glowing in the intense stellar radiation. Deeper, you enter the photosphere, the visible cloud layer. But these are not water clouds. At 1,900 K, water cannot exist as liquid or ice. Instead, the clouds might be composed of corundum, aluminum oxide, sapphire and ruby dust, or iron compounds, or complex silicates. Lightning arcs between cloud layers, discharges more powerful than anything on Jupiter. The winds are beyond comprehension. Supersonic jet streams racing at 10 kilometers per second, 10 times faster than sound. You will be torn apart, incinerated, ionized instantly. This is no place for visitors. Thousands of kilometers down, the atmosphere transitions to liquid metallic hydrogen under immense pressure. And at the core, if a core exists, lies perhaps a rocky or icy kernel, the original planetary seed around which all this gas accumulated billions of years ago. Hat P 32b is 1,040 light-years away. We will never visit it. We will never send a probe through its atmosphere or sample its composition directly. But through transits and eclipses, through spectroscopy and modeling, we have learned its secrets. We know its size, mass, temperature, and composition. We understand its atmosphere, its winds, its weather. We've witnessed the extreme inflation that makes this planet unique. And yet mysteries remain. Why exactly is Hat P32b so inflated? Is it tidal heating, ohmic dissipation, or some combination? How does the stellar magnetic field affect the planet? What role does the eccentric orbit play? How much longer can the planet maintain this inflated state? Hat P32b teaches us that planets are more diverse, more extreme, more fascinating than we ever imagined. It challenges our theories, pushes the boundaries of planetary physics, and reminds us that the universe contains wonders far beyond our everyday experience. This is Hat P32b, the inflated giant, a hot Jupiter swollen to nearly twice Jupiter's size despite equal mass. A world that shouldn't exist, yet does. A reminder that understanding planets, even those we'll never touch, helps us understand the fundamental forces that shape matter, energy, and worlds throughout the cosmos. The observations continue. The planet orbits on, and slowly, measurement by measurement, we unlock the secrets of the inflated giants. I don't know about you, but I'm ready to calm things down a bit after that last one. Let's head on over to K2-3d, our temperate neighbor, in the search for habitable super-Earths. In May 2013, the Kepler mission, which had discovered thousands of exoplanets, appeared to be ending. With only 2 functioning reaction wheels, the spacecraft could no longer maintain the precise pointing needed for planet detection. But engineers refused to give up. They devised an ingenious solution: use the pressure of sunlight itself as a virtual reaction wheel, allowing Kepler to observe new regions of the sky every 80 days. The K2 mission was born, Kepler's second life. Among K2's earliest discoveries was a nearby planetary system that would become one of the mission's most significant finds. K2-3, a small red dwarf star just 144 light-years away, hosting at least 3 planets. The outermost, K2-3d, orbits in the habitable zone, the region where temperatures could allow liquid water to exist on a rocky surface. K2-3d is not Earth. It's larger, a super-Earth, perhaps 50% bigger than our planet. Its star is smaller, cooler, dimmer, an M-dwarf that will shine for trillions of years. But K2-3d represents something profound, a potentially habitable world orbiting one of the most common stars in the galaxy, close enough to study in detail. K2's Campaign 0, its first science observation period, ran from March 8th to May 27th, 2014, observing approximately 21,600 target stars to test the new mission concept. Among these stars was EPIC 201367065, later designated K2-3. K2-3 was selected as a target because it's a nearby M dwarf, spectral type M0, relatively bright for a red dwarf, making it excellent for planet searches and follow-up studies. The automated pipeline detected multiple periodic transit signals, clear evidence of at least 3 planets transiting the star with periods of 10, 24, and 45 days. The discovery was announced in January 2015 as part of the first major release of K2 planet candidates. 3 planets, all larger than Earth but smaller than Neptune, all orbiting within 0.2 AU of their star. But it was the outermost planet, K2-3d, that captured immediate attention. The K2-3 system was recognized immediately as scientifically valuable. The star is nearby and relatively bright. The planets span interesting sizes. And most importantly, K2-3d orbits in or near the habitable zone. We conducted intensive follow-up observations using ground-based telescopes, photometry to refine transit parameters, spectroscopy to characterize the host star, high-resolution imaging to rule out stellar companions. The planets were validated through statistical methods and the absence of plausible false positive scenarios. By mid-2015, all 3 planets were confirmed. K2-3, also designated EPIC 201367065, is an M0V red dwarf, at the larger and hotter end of the M dwarf spectrum, but still much smaller and cooler than the Sun. K2-3 is an excellent host star for planet searches and habitability studies. It's an M0 dwarf, the largest and hottest M dwarf subtype, which means it's more Sun-like than the smallest M dwarfs. It's old enough to be stable, not showing the extreme flaring activity of younger M dwarfs. And critically, it's only 144 light-years away, close enough that detailed atmospheric characterization might be possible with JWST or future telescopes. The habitable zone, the orbital distance where liquid water could exist on a planet's surface, depends on stellar luminosity. 4 M dwarfs like K2-3, with only 6% of the Sun's luminosity, the habitable zone is much closer to the star. For K2-3, the habitable zone extends roughly from 0.14 to 0.28 AU, much closer than Earth's 1 AU orbit around the Sun, but the star is so much dimmer that planets at these distances receive similar radiation levels to Earth. The inner edge is defined by the runaway greenhouse limit, where water vapor creates uncontrolled warming like Venus. The outer edge is where CO2 condensation limits greenhouse warming. But habitable zones around M dwarfs present unique challenges. Planets must orbit close to receive sufficient warmth, making tidal locking likely. Stellar flares, though rarer on mature M dwarfs like K2-3, can still pose threats to atmospheric retention and surface habitability. The K2-3 system contains at least 3 confirmed planets, all detected through transits by K2. Each planet tells part of the system's story. K2-3b, innermost planet. K2-3c, middle planet. K2-3d, outermost confirmed planet, with 3d being in the habitable zone. What makes the K2-3 system fascinating is its architecture. 3 planets in compact, nearly circular orbits, likely coplanar. The planets increase in size from inner to outer. K2-3c is smaller than K2-3b, which might reflect different formation histories or atmospheric retention. And K2-3d, despite being the largest, has the highest density, suggesting it's the most rocky of the 3. K2-3d stands out as one of the most potentially habitable planets discovered by K2. Its properties place it firmly in the category of targets for future atmospheric characterization. K2-3D's density of 6.4 g/cm superscript 3 is particularly interesting. This is higher than Earth's density, suggesting either an iron-rich core comprising a large fraction of the planet's mass, or high internal pressures compressing a more typical rocky composition. At 1.51 Earth radii, K2-3D sits just at the upper edge of what we consider rocky planets, the radius-valley boundary around 1.5 to 1.6 Earth radii. This suggests K2-3D is likely predominantly rocky, with at most a thin atmosphere. K2-3D receives about 1.4 times the stellar flux that Earth receives from the Sun, more radiation than Earth, but less than Venus's 1.9 times Earth's flux. This places K2-3D near the inner edge of the conservative habitable zone, but comfortably within the optimistic habitable zone. The habitable zone has fuzzy boundaries. The conservative zone is where we're quite confident liquid water could exist. For K2-3, this extends from about 0.18 to 0.28 AU, and K2-3D at 0.21 AU sits right at the inner edge. The optimistic zone includes regions where liquid water might exist under favorable atmospheric conditions. This extends from 0.14 to 0.28 AU, and K2-3D is comfortably within it. Whether K2-3D can support liquid water depends critically on its atmosphere. Too much CO2 or water vapor in a runaway greenhouse effect like Venus could render the surface uninhabitable. Too thin an atmosphere, and the surface would be frozen despite the stellar radiation. The right balance, a moderate atmosphere with greenhouse warming, could create temperate conditions. At 0.21 AU from its star, K2-3D almost certainly experiences tidal locking, a process where tidal forces synchronize the planet's rotation period with its orbital period, creating permanent day and night hemispheres. Tidal locking was once thought to be a deal-breaker for habitability. The permanent day side would be scorching, the permanent night side frozen, and atmospheres might collapse as gases condense on the night side. But climate models have shown that if a planet has sufficient atmospheric mass, more than about 0.1 bar, winds redistribute heat from day to night, creating habitable conditions, potentially across the entire planet. On a tidally locked world, the star would hang motionless in the sky on the day side, appearing about 3 times larger than the Sun appears from Earth, but only 1/6 as bright. The sky would have a reddish hue. At the terminator, the boundary between day and night, conditions might be most temperate, with perpetual sunset or sunrise. To understand K2-3D's composition, whether it's rocky like Earth or has a thick volatile envelope, astronomers needed to measure its mass through radial velocity observations. We used the IRD spectrograph on the Subaru telescope and other instruments to measure K2-3's radial velocity, the star's wobble caused by the planet's gravity. For K2-3D, the semi-amplitude of the radial velocity signal is about 1.5 meters per second. Very small, challenging to detect. We needed dozens of precise measurements to extract the signal from stellar noise. The measurements confirmed K2-3D's mass at approximately 2.6 Earth masses. Combined with the radius of 1.51 Earth radii, this gives a density of 6.4 g/cm superscript 3, definitively rocky, with little room for a thick hydrogen-helium envelope. The high density rules out many Neptune scenarios. K2-3D is not a small gas planet. It's a genuine super-Earth, probably with an iron-silicate composition like Earth's, but possibly with a larger iron core or higher internal pressures. There might be a thin atmosphere, nitrogen, oxygen, CO2, water vapor, but no thick hydrogen envelope obscuring a solid surface. With mass and radius known, scientists can model K2-3D's internal structure. Possible interior compositions. Scenario 1. Earth-like composition. Iron core, 32% of radius versus Earth's 17%. Rocky mantle, silicate minerals. Thin crust. Possible atmosphere, less than 1% of mass. Surface gravity, 1.14 g. Scenario 2. Iron enriched. Larger iron core, 40% of radius. Thinner rocky mantle. Could result from giant impact, stripping mantle material. Higher density from extra iron. Surface gravity, 1.14 g. Scenario 3. Water world. Rocky core, 60% of radius. Water layer, 20% of mass. Possible high-pressure ice phases at depth. Steam/water vapor atmosphere. Surface gravity, 1.14 g. The high density favors iron-enriched or Earth-like compositions over water-world scenarios, though we can't rule out modest water content, perhaps 10 to 20% by mass. Interior modeling suggests K2-3D likely has active plate tectonics, a molten core generating a magnetic field, and geological activity, all favorable for long-term habitability. K2-3D checks many boxes for habitability, but significant uncertainties remain. Favorable factors. Orbital location. Within the optimistic habitable zone, receiving similar stellar flux to Earth, 1.4 times Earth's. Rocky composition. High density confirms predominantly rock-iron composition, likely with solid surface. Sufficient mass. At 2.6 Earth masses, strong enough gravity to retain atmosphere over billions of years. Mature, quiet star. K2-3 is old enough to be stable, not producing excessive flares that could strip atmospheres. Potential for magnetic field. Likely molten core could generate protective magnetic field. Nearby for study. Only 144 light-years away. Close enough for detailed follow-up observations. Challenging factors. Higher stellar flux. 1.4 times Earth's flux. Risk of runaway greenhouse if atmosphere too thick. Tidal locking. Permanent day/night hemispheres create extreme temperature gradients without sufficient atmosphere. M-dwarf environment. Stellar flares, though infrequent on mature M-dwarfs, could still affect habitability. Unknown atmosphere. We don't yet know if K2-3D has an atmosphere, what it's made of, or how thick it is. K2-3D is tantalizing but unconfirmed. It has the right size, mass, and orbital distance. The star is suitable, but we don't know the most critical factor, its atmosphere. Does it have one? Is it thick enough to redistribute heat? Does it contain water? Is there a runaway greenhouse, or are conditions temperate? These questions can only be answered through observations. Without direct observations, we can only model potential atmospheric scenarios based on what we know about terrestrial planet atmospheres. Scenario 1. Temperate with moderate atmosphere. Nitrogen-dominated atmosphere with CO2 and water vapor. Surface pressure, 0.5 to 2 bar, comparable to Earth. Greenhouse warming raises surface temperature to 270 to 320 K. Liquid water oceans possible. Life-supporting conditions plausible. Scenario 2. Runaway greenhouse, Venus-like. Thick CO2 atmosphere, 90 plus bar. Extreme greenhouse warming, 600 to 800 K. No liquid water, too hot. Possibly triggered by higher stellar flux. Uninhabitable. Scenario 3. Thin atmosphere, Mars-like. Thin CO2 atmosphere, less than 0.01 bar. Limited greenhouse warming. Surface temperatures, 200 to 270 K. Water, mostly frozen except possibly at dayside hottest points. Limited habitability. Scenario 4. Water-rich atmosphere. Thick water vapor and steam. High humidity, extensive clouds. Surface pressure, 5 to 50 bar. Possible global ocean beneath thick atmosphere. Uncertain habitability, extremes of temperature and pressure. Which scenario is correct depends on K2-3D's formation history, volcanic outgassing rates, atmospheric loss processes, and stellar irradiation history. We simply don't know yet, but JWST and future telescopes might tell us. Detecting and characterizing K2-3D's atmosphere is challenging but potentially possible with the James Webb Space Telescope. K2-3D is a difficult target for JWST. The host star is relatively faint, magnitude 12.2, and K2-3D is not as large as some sub-Neptunes, making atmospheric signals weaker. But it's doable. Transmission spectroscopy during transits could detect the presence of water vapor, carbon dioxide, methane, or molecular nitrogen features. We'd need multiple transits to accumulate sufficient signal, but it's within JWST's capabilities. As of current knowledge, comprehensive JWST observations of K2-3D have not been published, though the planet is likely on target lists for future observing cycles. The scientific community waits with anticipation for results that could reveal whether this potentially habitable world actually has an atmosphere conducive to life. K2-3D's significance extends beyond a single planet. It represents a test case for habitability around M-dwarf stars, the most common stellar type, comprising 75% of all stars in the galaxy. If habitable zone planets around M-dwarfs can support life, the number of potentially inhabited worlds in the galaxy increases dramatically. M-dwarfs are common, long-lived, trillions of years, and surveys show they frequently host small planets. K2-3D is one of the nearest potentially habitable M-dwarf planets, making it an ideal target for testing habitability theories. K2-3D is one of K2's most significant habitability discoveries, but the mission found hundreds of planets during its 4-year extended mission. K2 discovered over 500 confirmed planets and thousands of candidates. The mission's diversity, observing different fields every 80 days, meant we sampled different stellar populations. We found planets around young stars, old stars, binary stars, cluster stars. K2-3D shows that even a crippled spacecraft, creatively repurposed, can make discoveries that advance our search for habitable worlds. K2-3D and planets like it are driving the development of future observatories specifically designed to characterize habitable zone planets. Future capabilities: JWST extended observations, multiple transit observations to detect atmospheric features, constrained composition, search for biosignatures. Extremely large telescopes, YLT, GMT, TMT. Ground-based 30 to 40-meter telescopes achieving high-resolution spectroscopy, potentially detecting molecular oxygen directly. Plato, planetary transits, and oscillations of stars. ESA mission launching 2026, finding and characterizing planets around bright stars with better precision than K2. Habitable Worlds Observatory. Proposed NASA flagship mission for the 2040s, designed to directly image and characterize dozens of Earth-like planets, including atmospheric biosignature detection. K2-3D is close enough and interesting enough that it will remain a priority target for decades. Each new facility will reveal more details. JWST might detect its atmosphere. YLTs might measure its composition. Future missions might directly image it. K2-3D represents the kind of world we'll study intensively in our search for life beyond Earth. 144 light-years from Earth, in the constellation Aquarius, K2-3D continues its orbit. Every 44.5 days, it completes another circuit around its small red star. One hemisphere basks in constant red-orange starlight. The other faces eternal night. Between them, the Terminator, perpetual sunset, perpetual sunrise. We don't know what K2-3D looks like. Is there an ocean reflecting the red light of its star? Are there continents, mountains, valleys carved by ancient rivers? Are there clouds drifting in the eternal twilight at the Terminator? Is there rain, wind, seasons despite the tidal locking? Or is K2-3D barren, a lifeless rock with a thin atmosphere or no atmosphere at all, surface conditions too extreme for water, let alone life? We know K2-3D is real. We know its size and mass. We know it orbits in the habitable zone. We know it's rocky, but we don't know if it's habitable. We don't know if life exists there. We don't know if we're looking at a second Earth or another Venus. Within the next decade, we might know. JWST or future telescopes might detect K2-3D's atmosphere or confirm its absence. We might measure water vapor, carbon dioxide, oxygen. We might find evidence that this world, orbiting a star smaller and cooler than our sun, has conditions suitable for life. K2-3D reminds us that Earth-like worlds might be common, that around small red stars like K2-3, which comprise 3/4 of all stars, planets in habitable zones might be abundant, that within a few hundred light years, there might be dozens or hundreds of potentially habitable worlds. And K2-3D reminds us that these worlds are within reach, not to visit perhaps, but to study, to understand, to determine whether they harbor life. This is K2-3D, the temperate neighbor, a super-Earth in the habitable zone of a nearby red dwarf, a world that might have oceans, that might have an atmosphere, that might be home to life. A reminder that the search for habitable worlds has brought us tantalizing close to an answer, that the planets we seek exist, that they orbit nearby, and that understanding them is within our grasp. The research is ongoing. The planet orbits on, and soon, perhaps within our lifetimes, we will know whether K2-3D is habitable, whether it has the ingredients for life, and whether Earth's story has been repeated elsewhere in the universe. For our next world, let's check out WASP-83b and better understand diversity of hot Jupiters. In the constellation crater, 330 light-years from Earth, orbits a planet that tells a different story from many of its hot Jupiter cousins. WASP-83b, a gas giant slightly more massive than Jupiter, orbiting its star every 4.97 days in perfect alignment with the star's rotation. While many hot Jupiters show wildly misaligned or even retrograde orbits, evidence of violent migration through gravitational chaos. WASP-83b's orbit is orderly, aligned, suggesting a gentler journey from the outer solar system to its current close orbit. WASP-83b is not the hottest hot Jupiter. It's not the largest, nor the most inflated, but it represents something equally important: the diversity of hot Jupiter formation and migration pathways. Every aligned orbit tells us that not all hot Jupiters experienced violent scattering. Some migrated smoothly through their protoplanetary disks, preserving their alignment and offering insights into gentler planetary migration. The wide-angle search for planets, WASP, operates 2 robotic observatories, SuperWASP North in the Canary Islands and SuperWASP South in South Africa. Together, they monitor hundreds of thousands of stars across both hemispheres, searching for the periodic dimming that betrays transiting planets. WASP-83 was observed by SuperWASP North between 2007 and 2011. The automated pipeline detected periodic transits every 4.97 days with a depth of about 1.6%, indicating a large planet, roughly Jupiter-sized, orbiting close to its star. The star itself, magnitude 12.9 in V-band, was bright enough for detailed follow-up studies, but faint enough that no one had paid it particular attention before. The signal was clear and consistent across multiple observing seasons, ruling out instrumental artifacts or stellar variability. By 2012, WASP-83 was flagged as a high-priority candidate for follow-up confirmation. Confirming WASP-83b and measuring its properties required extensive ground-based observations using some of the world's largest telescopes. We used the Corley spectrograph at La Silla Observatory in Chile and the SOFI spectrograph at Haute-Provence Observatory in France to measure radial velocities. The stellar wobble amplitude, about 160 meters per second, confirmed a planetary mass of approximately 1.18 Jupiter masses. Combined with a radius of 1.04 Jupiter radii from transit observations, we calculated a density close to Jupiter's, suggesting a typical hot Jupiter composition. High-resolution imaging using adaptive optics ruled out stellar companions that could cause false positive transit signals. Spectroscopic analysis characterized the host star's properties, temperature, metallicity, age. By 2015, all data converged. WASP-83b was confirmed as a hot Jupiter orbiting a bright F-type star, officially announced in the scientific literature. WASP-83 is an F-type star, hotter, more massive, and more luminous than the Sun, creating an intense radiation environment for any close-orbiting planet. WASP-83 is a good example of an F-type star hosting a hot Jupiter. These stars are massive enough to have vigorous convective zones when young, potentially affecting planetary migration and magnetic interactions. They're also luminous enough that planets receive significant stellar radiation, heating their atmospheres and causing inflation. And they're bright enough for detailed atmospheric characterization. One of the most intriguing discoveries about WASP-83b came from measuring its spin-orbit alignment, whether the planet's orbital plane is aligned with the star's rotational equator. We used the Rossiter-McLaughlin technique, observing how the planet's transit affects the star's apparent radial velocity. As the planet crosses the star's rotating disk, it blocks light from the approaching side, then the receding side, creating a characteristic velocity pattern. For WASP-83b, the pattern showed the orbit is well aligned with the star's rotation. The spin-orbit angle is close to zero, indicating an aligned system. This alignment is significant. Many hot Jupiters, especially around hot stars, show misaligned or even retrograde orbits, evidence that they migrated inward through violent dynamical scattering with other planets or stellar companions. WASP-83b's aligned orbit suggests a different migration pathway, smooth migration through the protoplanetary disk, preserving the original alignment between the planet's orbit and the star's rotation. Aligned systems tell us that disk migration, where the planet spirals inward through gravitational interactions with the gas disk, can successfully deliver hot Jupiters to close orbits without disrupting the system's architecture. This has important implications for understanding planetary system formation and the frequency of different migration mechanisms. WASP-83b is classified as a hot Jupiter, a gas giant orbiting extremely close to its star, resulting in high temperatures and atmospheric inflation. WASP-83b is interesting precisely because it's relatively typical for a hot Jupiter. It's not extremely inflated like some hot Jupiters. Its radius is only 4% larger than Jupiter's despite receiving intense stellar radiation. This suggests efficient cooling or relatively modest atmospheric heating. It's massive enough to have strong gravity, which helps retain the atmosphere and resist inflation. And its temperature, around 1,450 K, places it in the mid-range for hot Jupiters. One of the puzzles of hot Jupiter science is atmospheric inflation. Why some planets are extremely puffy with densities far below Jupiter's, while others remain compact despite intense heating. WASP 83b has a density of 1.06 g/cm superscript 3, only slightly lower than Jupiter's 1.33 g/cm superscript 3. Given that it receives far more stellar radiation than Jupiter, about 600 times what Jupiter gets from the Sun, we might expect more significant inflation. The modest inflation suggests that whatever heating mechanisms are at work, ohmic dissipation, kinetic energy deposition, tidal heating, they're not as efficient on WASP 83b as on more inflated hot Jupiters. Several factors might explain this. The planet's relatively high mass means stronger gravity, which resists inflation. The circular orbit means minimal tidal heating from orbital eccentricity. And the atmospheric composition, specifically the absence or low abundance of certain optical absorbers, might reduce heating efficiency. At 1,450 to 1,500 K, WASP 83b is hot enough that most molecules dissociate into atoms, but not so hot that even refractory materials vaporize. WASP 83b's temperature places it in an interesting regime. It's hot enough that water molecules break apart into hydrogen and oxygen. Methane is completely destroyed, but it's cool enough that molecules like carbon monoxide, titanium oxide, and vanadium oxide can survive in certain atmospheric regions. This temperature also means we might see both clear atmospheric windows and regions with cloud formation. Like all close-orbiting planets, WASP 83b is almost certainly tidally locked. The day side, receiving constant stellar radiation, might reach 1,700 to 1,800 K. The night side, receiving no direct starlight, cools to perhaps 1,000 to 1,200 K. Powerful winds redistribute this heat, preventing even more extreme contrasts. WASP 83b's relatively large size, bright host star, and moderate temperature make it an accessible target for atmospheric characterization through transmission spectroscopy. Transmission spectroscopy works by measuring the planet's apparent size at different wavelengths during transit. Molecules in the atmosphere absorb specific colors of light, making the planet appear larger at those wavelengths. For WASP 83b, observations with Hubble's WFC-3 and STEES instruments, as well as ground-based spectrographs, have revealed atmospheric features indicating the presence of specific molecules and aerosols. Observations of WASP 83b have detected several atmospheric constituents, though with varying degrees of confidence. Key atmospheric detections and features. Water vapor, H2O. Evidence for water vapor features in the near-infrared spectrum, though somewhat muted compared to cloud-free models, suggesting high-altitude hazes or clouds partially obscure the signal. Sodium and potassium. Possible detections of alkali metal absorption features in the optical spectrum, though the signals are weaker than expected, again suggesting aerosol obscuration. High-altitude hazes or clouds. The overall spectral slope and muting of molecular features indicate the presence of high-altitude aerosols, either photochemical hazes, complex organic particles, or silicate/mineral clouds. Hydrogen and helium, dominant atmospheric constituents, as expected for a gas giant, inferred from mean molecular weight calculations rather than direct spectroscopic detection. Carbon monoxide, likely present based on equilibrium chemistry models for this temperature range, though definitive detection requires higher spectral resolution. WASP 83b's atmosphere appears to have a partially cloudy or hazy upper layer that obscures some molecular features. This is common for hot Jupiters in this temperature range. Around 1,450 K, various cloud-forming species like silicates can condense at specific atmospheric levels. Understanding the cloud composition and distribution helps us model atmospheric circulation and heat transport. Clouds are both fascinating and frustrating for exoplanet researchers. They tell us about atmospheric chemistry and dynamics, but they also obscure the deeper atmosphere where most molecules exist. On WASP, 83b, at temperatures around 1,450 K, we expect several types of clouds. Silicate clouds, composed of vaporized rock that condenses into tiny droplets, form at specific temperature-pressure levels. Aluminum oxide, corundum, clouds might form at slightly higher altitudes. And photochemical hazes, created when UV light breaks apart hydrocarbons, can accumulate in the upper atmosphere. These clouds scatter light, muting molecular absorption features. The clouds on WASP 83b likely aren't uniform. On the hot day side, high temperatures might vaporize most cloud particles. On the cooler night side, clouds condense and persist. At the terminator, the boundary between day and night, where transmission spectroscopy probes the atmosphere, clouds might be patchy, creating complex spectral signatures. While transit observations probe the atmosphere's limb, eclipse observations measure thermal emission from the planet's day side, providing complementary information about temperature and heat distribution. Spitzer observations at 3.6 and 4.5 microns during secondary eclipse detected WASP 83b's thermal emission. The brightness temperature, derived from how much infrared light the planet emits, is consistent with models predicting dayside temperatures around 1,700 to 1,800 K. The planet is efficiently radiating heat, suggesting moderate heat redistribution from day to night. WASP 83b's atmosphere is in constant motion, driven by the extreme temperature contrast between the permanently illuminated day side and the dark night side. Our circulation models for WASP 83b predict eastward equatorial jet streams, supersonic winds reaching 3 to 5 kilometers per second, transporting heat from the hot day side toward the cooler night side. These jets create a hotspot offset eastward from the substellar point by perhaps 20 to 40 degrees. The winds also drive vertical motion, updrafts on the day side, downdrafts on the night side, creating complex three-dimensional circulation patterns. The efficiency of heat redistribution affects the day-night temperature contrast. Eclipse observations suggest WASP 83b has moderate redistribution, not as efficient as some hot Jupiters where night-side temperatures approach day-side temperatures, but better than planets with minimal heat transport where the night side is extremely cold. The temperature difference between day and night doesn't just affect winds, it affects chemistry. On WASP 83b's day side, at 1,700 to 1,800 K, most molecules that can form are destroyed by thermal dissociation or photodissociation from stellar UV radiation. The atmosphere is mostly atomic, free hydrogen, helium, traces of atomic metals. But on the night side, at 1,000 to 1,200 K, molecules like carbon monoxide, water vapor, if oxygen is available, and various metal oxides can form. Winds transport gas between these regions, creating a chemical cycle. This day-night chemical asymmetry affects what we observe. Transmission spectroscopy at the terminator samples intermediate conditions. Molecules are partially dissociated, clouds are patchy, creating the complex spectra we detect. One question about WASP 83b is whether its atmosphere exhibits a temperature inversion, a layer where temperature increases with altitude rather than decreasing. Temperature inversions are caused by molecules like titanium oxide, vanadium oxide, or certain hazes that absorb optical and UV light from the star, heating the upper atmosphere. WASP 83b's temperature, around 1,450 K, is in a range where these molecules could exist. Eclipse spectroscopy data are somewhat ambiguous, but suggest a possible weak temperature inversion. More observations, particularly with JWST, are needed to confirm. WASP 83b is one of over 400 known hot Jupiters. What does it tell us about this diverse population? Hot Jupiters span a huge range of properties. WASP 83b is interesting because it's relatively normal, moderate temperature, typical density, aligned orbit. This normality is itself informative. It shows that disk migration can successfully produce aligned hot Jupiters with typical properties. It provides a comparison point for more extreme systems, and it demonstrates that hot Jupiters aren't all inflated, misaligned, or ultra-hot. Each hot Jupiter teaches us something different about formation, migration, and evolution. WASP 83b specifically illuminates the typical hot Jupiter pathway: disk migration preserving alignment, moderate heating and inflation, stable atmospheric structure. One of the most important discoveries in hot Jupiter science is the dichotomy between aligned and misaligned systems. When we measure spin-orbit angles for many hot Jupiters, we find a pattern. Planets around cool stars, spectral types late F, G, K, M, tend to have aligned orbits. Planets around hot stars, early F and A-type stars, show a wide range of alignments, including many misaligned and retrograde orbits. WASP 83, an F7 star right at the boundary, has an aligned system. This fits the pattern and suggests disk migration was the dominant mechanism. The pattern arises because hot stars lack the strong magnetic fields and tidal dissipation mechanisms that can realign misaligned orbits over time. Cooler stars can realign planets that arrived through dynamical scattering, but WASP 83b's alignment suggests it never experienced violent scattering. It migrated smoothly from birth. WASP 83b's properties: aligned orbit, circular orbit, typical density, tell a coherent story about its formation and journey to its current location. WASP 83b likely formed in the outer protoplanetary disk, several AU from the star, where temperatures were low enough for ice to condense and gas to accumulate efficiently. After forming, it migrated inward through Type II migration, gravitational interactions with the gas disk. The migration was smooth, preserving the planet's alignment with the stellar equator. Tidal forces from the star gradually circularized the orbit and tidally locked the planet's rotation. This pathway is thought to be common, perhaps dominant, for producing hot Jupiters. But not all hot Jupiters follow this path. Misaligned and eccentric systems show that dynamical scattering also occurs. WASP 83b represents the standard pathway, providing a baseline for comparison. The James Webb Space Telescope promises to revolutionize our understanding of WASP 83b and hot Jupiters like it. JWST's infrared instruments, NIR-SPEC, NIRIS, MIRI, can observe WASP 83b from 1 to 12 microns with far better sensitivity and spectral resolution than Hubble or Spitzer. Will detect molecules definitively: water, carbon monoxide, carbon dioxide, methane if present, potentially sulfur compounds, or metal oxides. Will measure abundances precisely, constraining atmospheric metallicity and Karov ratios. And will map temperature structure through eclipse spectroscopy. Planned JWST observations. Transmission spectroscopy. High-resolution spectra from 0.6 to 5 microns, detecting molecular features, constraining cloud properties, measuring abundances. Eclipse spectroscopy. Thermal emission spectra from 1 to 12 microns, mapping dayside temperature structure, detecting temperature inversions, constraining heat redistribution. Phase curve observations. Monitoring brightness throughout the orbit to map three-dimensional temperature distribution, track hotspot location, measure atmospheric circulation efficiency. Time series monitoring. Repeated observations searching for variability in atmospheric features, potentially detecting weather or cloud evolution. Ground-based, extremely large telescopes will complement JWST's observations with high-resolution spectroscopy revealing atmospheric dynamics. High-resolution spectroscopy from 30 to 40-meter telescopes like the YLT, GMT, or TMT can resolve individual molecular lines Doppler shifted by atmospheric winds. For WASP 83b, we can measure wind velocities directly, mapping the atmospheric circulation in 3 dimensions, detecting vertical motions, potentially even measuring the planet's rotation rate if it's not perfectly tidally locked. Long-term monitoring of WASP 83b can reveal changes over time, variations in stellar activity affecting the planet, possible atmospheric variability, and precise orbital evolution. By observing WASP 83b repeatedly over years, we can search for transit timing variations that might indicate additional planets in the system, monitor stellar activity cycles that could affect atmospheric observations, and track any long-term changes in the planet's properties. Such monitoring builds a comprehensive picture of the system's dynamics and evolution. 330 light-years from Earth, in the constellation crater WASP 83b continues its eternal orbit. Every 4.97 days, every 5 Earth days, it completes another circuit around its bright yellow-white star. The planet is massive, slightly more than Jupiter's mass. Yet it orbits 16 times closer to its star than Earth orbits the Sun. One hemisphere always faces the star, baking under constant radiation. The other faces eternal night, cooler but never truly cold. Imagine standing above WASP 83b's cloud tops, if such a thing were possible. The dayside would stretch before you, brilliant white yellow-orange from reflected starlight and thermal emission. Bands and zones circle the planet, driven by powerful winds. Clouds of exotic composition, silicates, metal oxides, drift at various altitudes, creating a layered, complex atmosphere. As you descended, you would pass through the haze layer, photochemical particles suspended in the thin upper atmosphere. Below, silicate cloud decks form and dissipate based on temperature and pressure. The temperature rises steadily, 1,400 K, 1,500 K, hotter still as you descend into the depths. The winds are beyond comprehension, kilometers per second, carrying heat from dayside to nightside, mixing the atmosphere, preventing even more extreme temperature contrasts. Lightning might arc through the clouds, discharges far more powerful than Jupiter's. Thousands of kilometers down, the atmosphere transitions from gas to liquid, then to exotic metallic states under crushing pressure. And somewhere below, perhaps, lies a core of rock and ice, the original planetary seed. WASP 83b will never be the most famous hot Jupiter. It's not the hottest, the largest, the most unusual, but it represents something equally valuable: normalcy. In a field dominated by extremes, planets being torn apart by tidal forces, atmospheres where iron reigns, orbits so misaligned they're retrograde. WASP 83b is the comparison point, the baseline, the example that shows what typical looks like. It shows us that hot Jupiters can form and migrate smoothly, preserving their alignment, that they can have moderate densities, neither extremely inflated nor unusually compact, that their atmospheres can be partially cloudy but not completely obscured, that they follow the patterns we expect from theory. And in that normalcy lies profound scientific value. Every extreme, hot Jupiter we study benefits from comparison to WASP 83b. Every theory we develop must explain both the extremes and the typical cases. WASP 83b anchors our understanding, reminding us that not all planets are outliers. This is WASP 83b, the aligned world, a hot Jupiter following the standard formation pathway, a planet with moderate properties that nonetheless reveals fundamental truths about how gas giants form, migrate, and evolve. A reminder that understanding the typical is just as important as understanding the extreme. That every planet, however normal, adds essential pieces to the puzzle of planetary diversity. The observations continue. The planet orbits on, and slowly, spectrum by spectrum, we understand not just WASP, 83b, but the entire population of hot Jupiters it represents. I hope you don't scare easily, because things are about to get dark. We'll be attempting to uncover, trace 2b, and the secrets of the blackest planet. 750 light-years from Earth, in the constellation Draco, orbits one of the most mysterious objects ever discovered. Trace 2b, a gas giant slightly larger than Jupiter, but unlike anything in our solar system. This planet is black. Not dark blue like Neptune. Not brown like Jupiter's storms. Black. It reflects less than 1% of the light that strikes it. Darker than coal. Darker than the blackest acrylic paint. Darker than anything we've encountered on Earth except specialized laboratory materials designed to absorb light. How can a planet be this dark? What atmospheric chemistry creates such extreme light absorption? And what does trace 2b's darkness reveal about the exotic processes occurring in hot Jupiter atmospheres? This is the story of the darkest known planet, a world that challenges our understanding of planetary atmospheres, light absorption, and the extremes that exist throughout the galaxy. The Transatlantic Exoplanet Survey, or TRACE, began operations in 2003 with a focused mission: find bright, transiting exoplanets suitable for detailed follow-up studies. Using 3 small 10-centimeter telescopes with wide-field cameras, TRACE monitored thousands of relatively bright stars, searching for the periodic dimming that betrays a transiting planet. TRACE 2 was designated GSE 03549-02811 in the star catalogs, a relatively bright star, magnitude 11.4 in V-band, visible in amateur telescopes. In 2006, our automated pipeline detected periodic transits every 2.47 days with a depth of about 1.5%, indicating a large planet, roughly Jupiter-sized, orbiting very close to its star. The transits were deep, clear, and consistent across multiple observing seasons. The discovery was announced in August 2006. TRACE 2b, only the second planet discovered by the TRACE survey, immediately stood out for its large size and bright host star, making it an excellent target for atmospheric studies. But no one yet suspected just how unusual this planet would prove to be. Confirming TRACE 2b required extensive follow-up using larger telescopes and precision instruments. We used the higher spectrograph at Keck Observatory to measure radial velocities, confirming a planetary mass of approximately 1.19 Jupiter masses. Combined with the radius of 1.17 Jupiter radii derived from transit observations, we calculated a density close to Jupiter's, indicating a typical hot Jupiter composition, mostly hydrogen and helium, with possibly a small rocky core. TRACE 2b appear to be a fairly typical hot Jupiter, massive, close-orbiting hot. At an equilibrium temperature around 1,500 K, it joined dozens of similar planets discovered in the preceding decade. What made TRACE 2b special would only emerge years later, through observations of a fundamentally different kind. When NASA's Kepler Space Telescope launched in March 2009, it was designed to stare continuously at one patch of sky containing about 150,000 stars, searching for Earth-sized planets through the transit method. By cosmic coincidence, TRACE 2, already known to host a transiting planet, was in Kepler's field of view. TRACE 2 wasn't a primary Kepler target. We already knew about the planet from ground-based observations. But having TRACE 2b in Kepler's continuous view provided an opportunity for unprecedented precision. Kepler's photometry was so precise, measuring brightness to parts per million, that we could detect subtle features in the transits and eclipses that revealed the planet's properties in extraordinary detail. While transit observations reveal a planet's size, eclipse observations, when the planet passes behind the star and its light is blocked, reveal how much light the planet reflects and emits. For most planets, eclipses show a combination of reflected starlight and thermal emission from the hot planet. The amount of reflected light depends on the planet's albedo, the fraction of incident light it reflects. In 2011, we analyzed Kepler's eclipse observations of Trace 2b, measuring how much the system's brightness decreased when the planet disappeared behind the star. The result was shocking. The eclipse depth was almost entirely due to thermal emission, the planet's own heat. There was almost no reflected light component. This meant Trace 2b's albedo was extraordinarily low, less than 1%, possibly as low as 0.1%. An albedo of less than 1% is almost unthinkable. For comparison, Earth reflects about 37% of incident light. Jupiter reflects 52%. The Moon reflects 12%. Even the darkest materials on Earth, coal, soot, asphalt, reflect 3 to 5% of light. Trace 2b reflects less than 1%. This planet is darker than coal, darker than any natural material on Earth. In visible light, it would appear almost completely black, barely distinguishable from the void of space, except for a faint red glow from its own heat. Trace 2 is what astronomers call a solar analog, a star remarkably similar to our Sun in mass, temperature, and composition. Trace 2 is one of the most Sun-like stars known to host a hot Jupiter. This makes Trace 2b particularly interesting for comparative studies. We can directly compare conditions on this close-orbiting giant to what would happen if Jupiter orbited our Sun at the same distance. The similarity also means Trace 2b receives nearly the same stellar spectrum as Jupiter would if moved closer, helping us understand how stellar radiation affects atmospheric chemistry. Trace 2b is classified as a hot Jupiter, a gas giant orbiting extremely close to its star, resulting in high temperatures and atmospheric heating. The darkness of Trace 2b is its defining characteristic. If you could somehow observe it next to Jupiter from the same distance, Jupiter would be brilliantly visible, reflecting half of the sunlight hitting it. Trace 2b would be almost invisible, a black sphere against black space, visible only as a faint red ember glowing from its own heat. It's one of the most alien worlds we've discovered. Understanding why Trace 2b is so dark requires understanding how planetary atmospheres reflect and absorb light. Albedo, reflectivity, depends on atmospheric composition, cloud properties, and molecular absorption. Most gas giants reflect a lot of light because their upper atmospheres contain ammonia clouds, water ice clouds, or hazes that scatter light efficiently. Trace 2b must have atmospheric properties that prevent cloud formation and maximize light absorption. Several atmospheric components could contribute to Trace 2b's extreme darkness. Proposed absorption mechanisms. 1. Alkali metals, sodium and potassium. Sodium and potassium have extremely strong absorption lines in the visible spectrum. At Trace 2b's temperatures, these metals exist as free atoms in the upper atmosphere. They absorb yellow and orange light efficiently, contributing to darkness. 2. Titanium oxide and vanadium oxide. These metal oxides absorb strongly across the visible and near-infrared spectrum. If present in high abundances in Trace 2b's atmosphere, they could absorb incident starlight before it can be reflected. 3. Light-absorbing hazes. Complex organic molecules, polycyclic aromatic hydrocarbons, or other photochemical products, created when UV light breaks apart methane and other hydrocarbons. These sooty particles absorb light across all visible wavelengths, similar to soot on Earth. 4. Absence of reflective clouds. Trace 2b is too hot for ammonia or water ice clouds that normally reflect light on cooler gas giants. Without these reflective layers, incident light penetrates deep into the atmosphere where absorbers trap it. The most likely explanation is a combination. Alkali metals absorb yellow-orange light. TO and VO absorb blue and near UV. Photochemical hazes absorb across all wavelengths. And critically, there are no high-altitude reflective clouds to scatter light back to space before these absorbers trap it. The result is almost perfect absorption. Light enters the atmosphere and never comes back out. While trace 2b reflects almost no light, it does emit thermal radiation, heat from the intense stellar irradiation, and possibly internal heat sources. At 1,800 to 2,000 K on the day side, trace 2b glows with its own thermal radiation, peaking in the near-infrared around 1.5 to 2 microns. In visible wavelengths, this manifests as a faint red glow, hot enough to be visible but much dimmer than reflected light would be. Kepler detected this thermal emission during eclipse observations, allowing us to calculate the dayside temperature. If you could see trace 2b directly, it would appear as a dark red ember, barely visible in red light from its own heat, but almost invisible in shorter wavelengths. The contrast between the bright star and the nearly invisible planet would be extreme. Trace 2b's extreme light absorption raises a puzzling question. Where does all that absorbed energy go? Trace 2b absorbs more than 99% of incident starlight, enormous amounts of energy. That energy must go somewhere. It can't just accumulate or the planet would continuously heat up. So it must be re-radiated as thermal emission, primarily in the infrared. Our models suggest trace 2b's atmosphere is very efficient at converting absorbed visible light into infrared heat, which then radiates to space. But the exact mechanisms, how quickly heat is transported downward, how atmospheric circulation distributes energy, remain unclear. Trace 2b's atmosphere is structured by temperature gradients driven by stellar heating and atmospheric circulation. On trace 2b's day side, temperatures reach 1,800 to 2,000 K at the top of the atmosphere, where stellar radiation is absorbed. Below, in the deeper atmosphere, pressure increases and temperatures rise further, potentially exceeding 2,500 K at depth. The night side, receiving no direct starlight, cools to perhaps 1,200 to 1,500 K, though winds transport heat from day to night, preventing more extreme cooling. The efficient light absorption affects temperature structure. Rather than being absorbed gradually throughout the atmosphere, most light is absorbed in the upper layers by alkali metals and metal oxides, creating a hot upper atmosphere. Potentially a temperature inversion where temperature increases rather than decreases with altitude. Trace 2b's atmosphere is in constant motion, driven by extreme day-night temperature contrasts. Our circulation models predict strong eastward equatorial jet streams, supersonic winds reaching 5 to 8 kilometers per second, transporting heat from the blazing day side to the cooler night side. These winds create a hotspot offset eastward from the substellar point. Vertical motions, updrafts on the day side, downdrafts on the night side, mix the atmosphere vertically, affecting temperature and composition profiles. The winds don't just transport heat, they also transport chemical species. Molecules that form on the night side can be carried to the day side where high temperatures destroy them. Atomic species created on the day side flow to the night side where they might recombine into molecules. This creates complex chemical disequilibrium throughout the atmosphere. Trace 2b presents radically different faces to the universe. The day side, temperature, 1,800 to 2,000 K at cloud tops. Appearance, deep red glow from thermal emission, almost no reflected light. Atmosphere, mostly atomic, molecules dissociated by heat and UV. Chemistry: alkali metals, TO, VO, atomic hydrogen and helium. Clouds: none, too hot for any condensates. Winds: strong updrafts carrying heat and chemical species upward. The night side: temperature 1,200 to 1,500 K. Appearance: dimmer red glow, cooling by thermal radiation. Atmosphere: some molecules can survive, CO, possibly small amounts of H2O. Chemistry: recombination reactions forming molecules from atoms. Clouds: possible metal oxide or silicate clouds at depth. Winds: downdrafts carrying cooled gas and condensed particles downward. One of the key questions about TRACE 2b's atmosphere is whether it has a temperature inversion, a layer where temperature increases with altitude. Temperature inversions are created when molecules like TO or VO or certain hazes absorb stellar UV and visible light high in the atmosphere, heating that layer. TRACE 2b's extreme light absorption, likely due to TO, VO, and light-absorbing hazes, suggests a strong temperature inversion is present. The upper atmosphere, where these species concentrate, could be several hundred degrees hotter than the layer just below. This affects atmospheric chemistry, cloud formation, and heat transport. Ironically, TRACE 2b's extreme darkness, its most interesting property, makes it difficult to study through traditional techniques. Transmission spectroscopy, measuring atmospheric absorption during transits, works best when the planet has strong molecular features. But TRACE 2b's atmosphere is dominated by absorbers, alkali metals, metal oxides, hazes that create broad, overlapping absorption across all visible wavelengths. This produces a relatively featureless spectrum that's difficult to interpret. Eclipse spectroscopy is more promising, measuring thermal emission, but TRACE 2b's host star is relatively faint, making high-precision observations challenging. Despite observational challenges, TRACE 2b has revealed important insights about hot Jupiter atmospheres. Confirmed findings: extreme low albedo, definitively measured at less than 1%, making TRACE 2b the darkest known exoplanet. Only specialized laboratory materials like Vantablack approach this level of light absorption. High dayside temperature. Thermal emission measurements confirm temperatures of 1,800 to 2,000 K, consistent with efficient absorption and re-radiation of stellar energy. Atmospheric composition. Strong evidence for alkali metals, metal oxides, and light-absorbing hazes in the atmosphere based on the extreme darkness and thermal properties. Efficient heat redistribution. Moderate day-night temperature contrast suggests moderately efficient atmospheric circulation transporting heat. Likely temperature inversion. Thermal properties and light absorption characteristics strongly suggest an inverted temperature structure with hot upper atmosphere. TRACE 2b is an outlier. No other planet approaches its extreme darkness. This tells us that the specific combination of atmospheric conditions on TRACE 2b, the right temperature, the right abundances of absorbing species, the absence of reflective clouds, is rare. Understanding why TRACE 2b is so dark helps us understand the full range of atmospheric properties hot Jupiters can have. The James Webb Space Telescope offers new opportunities to study TRACE 2b, focusing on infrared wavelengths where thermal emission dominates. JWST's infrared instruments, particularly NIR-SPEC and MIRI, can observe TRACE 2b's thermal emission during eclipses with far greater sensitivity and spectral resolution than Spitzer. We can detect molecules that emit in the infrared, water vapor, carbon monoxide, carbon dioxide, measure their abundances, and map temperature structure through emission spectroscopy. We can also observe phase curves, monitoring the planet's brightness throughout its orbit to map three-dimensional temperature distribution. Planned JWST observations. Eclipse spectroscopy. Detect molecular emission features, H2O, CO, CO2, measure atmospheric temperature structure, confirm/measure temperature inversion, constrain metallicity, and Kerr ratio. Phase curve observations. Map temperature distribution across the planet's surface. Measure heat redistribution efficiency. Track hotspot location and movement. Time series monitoring. Search for atmospheric variability. Detect possible weather patterns or cloud formation/dissipation cycles. Extremely large telescopes with adaptive optics and high-resolution spectrographs will provide complementary capabilities. High-resolution spectroscopy, or 100,000 from 30 to 40-meter telescopes, can resolve individual molecular lines Doppler shifted by atmospheric winds. For trace, 2B, we can directly measure wind velocities, mapping atmospheric circulation in 3 dimensions. We can detect molecules at high precision, definitively confirming TO, VO, and other absorbers responsible for the darkness. And we can search for disequilibrium chemistry, molecules that shouldn't be present based on equilibrium thermodynamics, but exist due to vertical mixing or photochemistry. Trace 2B's discovery raises an obvious question. Are there other planets this dark, or is Trace 2B unique? Measuring planetary albedos requires precise eclipse photometry, difficult for most planets. Kepler was uniquely suited to this because of its continuous, high-precision observations. TESS, Kepler's successor, is finding new transiting planets around brighter stars. For the brightest systems, we might be able to measure albedos and discover whether other Trace 2B, like dark worlds, exist. If they do, we can start understanding what conditions create such extreme darkness. If Trace 2B remains unique, that's equally informative. It tells us these conditions are rare. Imagine approaching Trace 2B across the void of space. At first, you see nothing, just a bright yellow star ahead. But as you draw closer, you notice something blocking the stars behind it, a shadow, darker than space itself. This is Trace 2B, a planet so dark it's almost indistinguishable from the emptiness around it. Only when you're very close does the faint red glow become visible. Thermal radiation from a world heated to 1,800 Kelvin, glowing like a barely visible ember. The planet looms before you, massive, larger than Jupiter, but appearing as little more than a black disk against black space. The star blazes nearby, 30 times larger in apparent size than the Sun appears from Earth. Yet Trace 2B absorbs all that light, drinking it in, reflecting almost nothing back. As you descend toward the day side, if such a journey were possible, you would enter an atmosphere unlike any in our solar system. The upper layers are filled with vaporized sodium and potassium, titanium oxide, vanadium oxide, complex organic hazes, all absorbing light across every wavelength. The sky would be deep red from the planet's own thermal emission, growing brighter as you descend and temperatures increase. Thousands of kilometers down, the atmosphere transitions from gas to liquid under crushing pressure, then to exotic metallic states. And somewhere far below, perhaps, lies a core of rock and ice, the seed around which this dark giant formed. Trace 2B is 750 light-years away. We will never visit it. We will never see it with our own eyes. But through the subtle dip in starlight during eclipses, through thermal emission measured in the infrared, through careful analysis of spectroscopic data, we have learned its profound secret. This is the darkest planet we have ever found. And that darkness teaches us something fundamental about planetary diversity. It shows us that planetary atmospheres can have properties we never imagined. That the same stellar radiation can create wildly different atmospheric conditions depending on composition and chemistry. That planets can exist at extremes we're only beginning to explore. Trace 2B reminds us that the universe contains wonders far stranger than our everyday experience suggests. A planet darker than coal. a world that absorbs nearly all light that strikes it. A giant wrapped in shadows, glowing faintly with its own heat, orbiting a sun-like star in a distant corner of the galaxy. This is Trace 2b, the dark world, the blackest known planet, a gas giant that challenges everything we thought we knew about planetary atmospheres and light absorption. A reminder that the cosmos is full of extremes, that planets come in configurations beyond our imagination, and that understanding these alien worlds, however dark, however distant, helps us understand the fundamental physics that shapes all planets, everywhere. The observations continue. The planet orbits on, shrouded in darkness, and slowly, measurement by measurement, we illuminate the secrets of the blackest world. If you made it all the way through this video, thank you so much. It really does mean all the world to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.